Okay, so welcome everybody. It's a great pleasure to have Pratik Rath from UC Santa Barbara. He's going to give us a set of 3 lectures. The first of which is today, and the next will be tomorrow at 11 a.m. And the third will be on Thursday at 10 a.m. But if the room is available later on, we might shift the Thursday lecture. Anyway, so it's a great pleasure, Pratik. So please take it.
Thank you so much. Firstly, thanks a lot for inviting me for these set of lectures. It's a great pleasure to be here at the IFR for these lectures. Secondly, so this set of lectures is intended as sort of an overview of this field of holography and tensor networks. It's sort of like viewing quantum gravity from a quantum information perspective, and I'd like to largely emphasize some of the work that I've been doing in the last few years. So the first talk today is about fixed area states, whose history starts from this paper with Chris Akers in 2018. But ever since then, there's a lot more that we've understood. So I'll talk about more recent work with these collaborators, which was last year, and then some more work that's in progress with Xidong and Don Marolf. And I should give a special thanks to both Xi and Don, from whom I've learned a lot about all of this. All right, so let me just give some broad motivation to lay down the framework. ADS-CFT is our most useful theory of quantum gravity that we understand reasonably well. It basically says that quantum gravity in d plus 1 dimensional ADS, which is this soup can, as we usually draw it, is equal to a conformal field theory in d dimensions, starting from Mandelsena in 1997 and 25 years of work ever since. So this was all good, and we usually viewed this from a perspective of computing scattering amplitudes, things that we usually do in high energy theory. But in the last 15 years or so, there's been a sort of shift in a different view of ADS-CFT, which is using ideas from quantum information theory. So starting from Ryu Takenagi, who in 2006 proposed that the entropy, the entanglement entropy of boundary subregions is related to areas in the bulk. A lot of stuff has started from that point, and it's usually colloquially called the it from qubit way of thinking about it. This has sort of given us a fine-grained perspective on ADS-CFT in the following sense. So what the Ryu Takenagi formula and its various generalizations tell you is that the entropy of a boundary region, let's call it R, is equal to the area of an extremal surface, the area over 4G of a surface gamma R, which is anchored to the endpoints of R, plus the bulk entropy of this green region, which is little r, which is sort of between gamma R and R. And the latest version of this is to take this combined sum and minimize over possible extremal surfaces or possible choices of gamma R. This is what's called the quantum extremal surface formula, or Island's formula. It goes under various names. And the latest success of this, as you might know, is the fact that it calculates for you the page curve of black hole evaporation. So this is something that for a long while we didn't understand how to do. And this formula at least gives us a semi-classical way to understand how the page curve of black hole evaporation happens. The sense in which, so following this chain of logic, starting with the Ryu Takenagi formula and so on, gives us a fine-grained view in the following sense. It basically tells us that there's a sub-region duality, which says that the information that you have in the boundary region capital R is dual to this green region little r, which is everything inside the quantum extremal surface gamma R.
Wait, Pratik.
Yeah.
I'm sorry, I'm in online. So actually the video is towards the
That's what I was saying. I
not
thought that the video is not showing the slides, but he said it was. That's sorry about that, Sachin. I think it's showing this screen.
Showing the blackboard, is it?
Oh, share screen. हाँ, share screen. वो था पहले. ठीक है? Sorry. Do you see it now?
Yes, thank you.
Sorry about that. So, okay. So I'll just, I'll just briefly say what I said again. We always knew that, we knew from Adesina's work that ADS equals CFD in the sense that everything inside the soup can equals everything on the boundary of it. But quantum information understanding told us that there's a more fine-grained sense in which this boundary region, any boundary region R, specifically encodes the information in this associated region little r, which is called the entanglement. Okay. Good. So now that was about ADS-CFD, which is what I mean by holography. But a large part of these lectures is going to be about talking about toy models of holography, which are not really ADS-CFD, but still have a lot of the features that we learned in ADS-CFD. And in fact, it's vice versa. We learned a lot about ADS-CFD starting from these toy models. So that's what I'd like to emphasize. So the toy models that I'd like to talk about are tensor networks. So tensor networks are the following. You can think about these pictures. So this is some graph which has vertices. So these blue dots are these vertices which are connected by some edges, which are these in-plane black legs. And further, it can have these yellow dots which are out of the plane legs, which you can think of as bulk degrees of freedom. And if we forget about the bulk legs, what these tensor networks do is essentially geometrize the entanglement structure of the boundary state. So the way these tensor networks came about initially was writing down a conformal field theory state in general is pretty complicated. The Hilbert space is pretty large. But tensor networks are a smart way of using the fact that the entanglement structure, so let's say you have a two-dimensional conformal field theory, the entropy, the entanglement entropy of a boundary region in the vacuum state is much smaller than the largest value it could have been. So it basically grows logarithmically with R and not in terms of a volume law with R. So you make the smart choice that you draw this graph such that the minimal cut through the graph, which is anchored to any given region, at most has a logarithmic number of legs. So it encodes this fact that the entanglement is bounded, and this gives you a much more optimal way of representing the CFD state. So it started as a numerical technique in condensed matter, where you could represent the state in this sense, where you just geometrized it based on what you know about the entanglement structure of that particular state. But in holography, yes, yeah.
What's the sort of more quantitative? I mean, what's the quantitative version of this law, logarithmic law?
So what the quantitative version is? So let's say you take a general tensor network, then the entropy of any given boundary region is bounded by the log of the dimension of all the edges that you cut on this gamma R. So the dimensions of, basically what happens is you can effectively represent the state on these legs, like you can push the state to these legs, and the Hilbert space that you're cutting through on this surface puts a bound on what the maximum value of the entropy can be.
So that's the bound.
That's a bound. So in a general tensor network, this is only a bound.
Yes.
In holography, this will be saturated. So it's actually an equality in holography. That will be important. But in general, it's just a bound.
So meaning that if this was really a quantum field theory,
Yes.
which is holographic,
Then it will be saturated. That's right.
Sorry, Pratik, I know I've already been bugging you earlier, but when you say it was shown, just to understand in condensed matter physics, so say Vidal and so on, just to understand, they showed that there was a systematic way of doing RG. Is it where you could develop a notion of this mirror with this property?
There are special cases where you can do it directly in that sense.
Okay.
More generally, what Vidal and collaborators did was they just, it was sort of physically motivated that entropies will only grow logarithmically, correlations will have power law behavior and so on. And so they just wrote down some network which would would give you those properties in this sense that like it's bounded by that. And then what you do is just try to optimize, just do like a variational principle, optimize those tensors to get you the right, like get you as close to the vacuum state or whichever state you like, as much as you can numerically. In certain cases, there's also what's called the continuum version of this, which is C-MERA, where you can actually, like for free field theories, for example, you can actually write down exactly how to get those, like what those tensors are. That's not always doable, it's a more complicated thing, but for some examples, we do.
So for an interacting conformal field theory, this is an uncontrolled approximation.
Yeah, I don't know if maybe there's some, maybe like phi cube or something where you can do it, but in general, no. In general,
You can't
it's
improve it systematically. In some
yeah, I don't know. At least not in a computationally tractable way that I know of. Like in principle, you could. There's like a lot of degrees of freedom in this network. So in principle, you could write down some huge thing and do like
a little like mean field theory. I mean, in logical status. You do it if it works, it works. If it doesn't, you can't do anything.
Yes. Is it? I thought in a way Pratik was saying is a variational. It's not
But variational within some answers. Right? The answers may be wrong.
But so what's known is that so if you have a CFT, I think it's known that the entropies will grow logarithmically.
Yeah, I mean, the
And-
Cardi formula.
yeah.
I imagine.
But for example,
So that of course.
and so this is.
So this you're putting into the thing, but there's
You're putting it into the
more than
thing.
entanglement entropy, right? In the solution to the theory.
Well, but this just guarantees you that there will be some solution which has this logarithmic growth. I mean,
Excellent. For instance, let me ask, what about the nth Renyi entropy?
yeah.
Does it get those bang on?
So good. So that was something I was eventually going to get to, but let me say it now. So there's a sense in which the entanglement entropy is a good observable in that small corrections to the state don't change the entanglement entropy too much.
Okay.
So if you've got the state itself pretty accurately on the boundary, then you're sure to get the entanglement entropy right as well. The Renyi entropies aren't like that. So the Renyi entropies are notoriously discontinuous. So if you just truncate some like tails of the wave function, you can change the Renyi entropies drastically. So that's not what's guaranteed. What's guaranteed here is that the state is pretty close. So you're guaranteed that correlation functions are similar. You're guaranteed that entanglement entropies are similar, but not necessarily
Pretty
Renyi
close is what
entropies. So I think you can talk about it in like the one norm distance. Like
No, but I mean, how can you make pretty close as 0.1 or 0.01 or is there a parameter? An approximation is good if there's a parameter which you can use and then
you do to the network to make it better.
to make it better. Yeah. I think so the parameter here, so in this case, like so in this case, it's like a discretized version anyway. So there's already some lattice cutoff. The parameter.
So is the boundary like 0 infinity or finite?
So normally the way this is done in condensed matter is you'll just take some finite thing and then take the just take it larger and larger, see what you get by extrapolation.
All the way up to the
Yeah.
boundary, but just cut it
You
off.
just cut it off at some point. In C-MERA, it really has an infinite number of degrees of freedom. But here what I'm drawing is like a discretization of it, like a lattice discretization.
Let me ask you something.
Yeah.
I know nothing about the subject, but tell me if it's roughly correct. I thought what Vidal and all tried to do was they, of course, discretize the field theory.
Yeah.
So there is a lattice scale.
Yeah.
And then more or less they had kind of a variational wave function. And they were able to show that, okay, the correlation functions, etc., come out reasonably correctly. Reasonable for Shiraz's point, I thought was, it's after all a lattice approximation.
Yes.
So the parameter is this lattice scale.
That's what I was getting to. I
Is
think
it
it's
is it
just
a theorem that you take that lattice scale to
Yeah.
infinity, to 0,
Yeah.
and you will get the exact answer? Is that a theorem?
I think in some cases that has been proved.
Meaning in free field theory.
Maybe even like weakly interacting or something, but I'm not exactly sure about the which.
Okay, but let's say we take Wilson-Fisher theory.
Yeah.
Is that a theorem for that?
I don't know. I won't claim it.
I mean, okay, sometimes proving an exact continuum limit even in...
No, not even a theorem. I mean, a theorem is too strong.
numerical-
Is there a good reason to believe
Good
it?
reason to believe.
Like, okay, yeah, good physical.
Good reason to believe for a physicist. A
I
theorem is...
think a good reason to believe this is So when we've cut it off at some scale, we expect that up to corrections of the order of that I mean, which is controlled by that lattice cutoff, the behavior of correlation functions or entanglement entropy has the behavior of the CFT, right? Like, I mean, there's power law decays in the correlation function and so on. That's something you can get out of this. I mean, anything which has logarithmic entropy can be written in terms of this network. And so in that sense, it's
lovely. But will the scaling dimensions come out exactly right?
That's what I was exactly.
So the Renyi entropies will not, for the reason I said before.
Renyi, let's not do. But what about this?
For the scaling dimensions,
Like the conformal bootstrap, gets the scaling dimensions very well.
Yes.
Can this get it?
Yeah.
Systematically improve.
I'm not sure about whether there's a theorem on this, but I think it's expected that it would. Because these are just.
Sorry, but what is the model-specific information you are putting into it when you ask about the dimension?
The model-specific information is you're just doing the variational principle. So you're just trying to minimize the energy. Like you have some Hamiltonian, you're trying to minimize the energy of states of this form, and you find the vacuum in that.
So you start with some Hamiltonian.
But you're choosing a particular form.
Yes.
That was what I felt is the arbitrary part.
That's right. So
it seems unlikely to me that you'll get bang on. Unless there's something I'm not seeing. Maybe it's true, but I don't.
Well, if the vacuum entanglement entropy is like logarithmic bang on, then I don't see why you won't get it. Like this has a lot of parameters.
But all conformal field theories have logarithmic entanglement entropy.
Yes.
There are many different conformal field theories. You have to get the right scaling dimensions for that particular kind.
Yeah, but this has a.
Oh, we can go on. I'm sorry to disrupt.
Yeah.
No, I mean just to understand what the status within field theory of this is before we get to holography.
Yeah. I'm not sure.
These descent, whatever goes in, you'll explain all this. Sorry.
Yeah.
For example, what little I know in Vidal's case is he tries to do the RG and he tries to, keep track of entanglement, right, carefully as he goes. So you do the RG like you would in lattice gauge theory by blocking, but then you keep track of entanglement. Now, when you do that, do you keep something about the theory in how you do the blocking and so on? Because that's how we would normally do
in this
theory.
Free field example, that's exactly what you do. You know exactly what course training you're doing when you're going from one field to another. In general, you don't. You just put it on a computer and you just find what numbers you get. And
Okay, but then the computer is...
The computer is doing that. But I guess there's a question of whether it's a controlled approximation in the sense that are you guaranteed
forget guaranteed, as Sandeep said, is a very strong word, which we don't normally use in physics.
Yeah.
I mean, is there a reasonable reason to believe? Like, the Wilsonian RG flow, is no guarantee maybe for a mathematician, but we all believe it. Is it like that, or is it worse than that?
Also, need is some large C type approximation.
So you don't. So this is something that I'd like to emphasize, which is when condensed matter people study this, you can study like whatever theory you like.
Right.
The difference is in what Gautam was asking about, which is in general you just get some bound on the entropy, which is bounded by those legs. In a large C theory, what the nice thing that tends to happen is that it gets saturated. So that's why it's a little special. But this is true nevertheless. Like you should still be able to represent the state in this case. I don't have I'm not sure of what the status is in terms of like there are how well known it is that this can be approximated for an arbitrary theory. I believe that for a general conformal field theory, it's expected, but I can't point you to a theorem.
Does the state-specific, theory-specific information go into what type of tensors you use?
Yeah, that's right. So what you do is you put in, so you have some Hamiltonian for that theory, and what you want to do is you look at all possible states that you generate like this. So the tensors are some like variable that you're changing, and you want to optimize over the energy. So let's say you want to find the vacuum state, then you just optimize over the energy, find the values of the tensors that give you the best energy. That's the best approximation to the vacuum.
I mean, it seems,
I think it's reasonable to expect that, but I don't have a theorem.
because, I mean, as long as you're able to generate a lot of states in a discretized approximation, you should be, believe that you,
Yeah, I think you're throwing away a lot of states in the sense that there's a lot of states with volume law entanglement, you're throwing all of them away,
Yeah.
but you're keeping all the states which have logarithmic entanglement. And as long as that's all you needed from your theory, then, I mean, even the ones which reproduce your correlation functions will be eventually something which have logarithmic growth of entropy. So they're one of these. So I think that's the reason we expect it, but I don't know if it's the theorem.
No, but okay, you must go on. But I mean, there's a reason why we believe Wilson's blocking procedure, right? Because when you do the blocking literally, you aren't throwing away the long wavelength information. You're just keeping it in a more efficient way.
Yeah.
And if it might not be so much to expect that one could prove something like that for an improved blocking where you keep entanglement. I mean, I thought that was the spirit of Mira.
Yeah, I guess you could say that, but I don't know if anything, I
It's
mean,
been
apart from
shown
free fields, like I don't think anything
Sure.
like that, it's hard to show something like that.
Okay.
Because these are like two different.
So, what do you mean by blocking?
So, the way Wilson first thought about the RG was you had this lattice. And then he said, instead of thinking of each unit cell on the lattice, I'm going to club two together and take that to be a unit cell. And that's what I mean by blocking. And then, of course,
Making blocks.
yeah, you make the blocks. And then you keep the information on the scale of the two unit cell accurately. Like that. So that would be a kind of argument that physicists would be okay with, right? Something like that, Sridhar is saying.
Yeah.
Okay.
Okay, Wilson preceded by Kadanoff.
Kadanoff.
Okay, sorry.
Okay, so should I go? So good. So that was from the condensed matter perspective. So that's where tensor networks really came from. But what I want to talk about here is more about in the context of holography. So in the context of holography, so firstly it was noted by Swingle that the logarithmic sort of this hyperbolic structure of this graph for the Mera network, for example, which reproduces the vacuum state, is precisely what you get in the ADS geometry, right? So there's a hyperbolic geometry, which is precisely looking like the Mera network that you would have gotten. And so he started with this connection, and then there were more examples of these tensor networks that were written down, which basically captured all the features of holography that we knew from this quantum information perspective, which is firstly the RT formula. So as I was saying before, in general, the entropy of R is just bounded by the area of gamma R, but you can have nice networks, which are what are called isometric networks, where there's a precise isometry between the state on these legs and the state on the boundary, which tells you that the entropy is actually equal to the area of that surface. And the area here just means the dimensions of the bonds that you're and that's basically what the RT formula is doing. It's computing the entropy by an area. And in fact, for some of these networks, which are like the random tensor network, you can actually get the full quantum extremal surface formula as well. So it was something that preceded any of these island calculations and so on.
By that, sorry, you mean including the matter?
Including the mass. So you can, with these yellow dots, you can add like these out of the plane legs, which you should think of as bulk degrees of freedom. The bulk degrees of freedom can have a general state. Then you should think about this tensor network as a map from some bulk state to a boundary state. So you can choose your favorite bulk state, which has some entropy, some entanglement structure, and then compute the entropy of the boundary state. That boundary state will be given by the entropy of that boundary state will be given by the quantum extremal surface formula.
So, Pratik, just one question. It's related to previous question. So, when you do this variation procedure for
Yeah.
Is there a reason to believe that the tensors at every node are the same?
It's so if you have like a translation symmetric theory, then you would.
Conformal theory.
It's a conformal theory, so then even more so. Like I'm just saying, even if you just had translation symmetry, already you would expect that.
But that you would not expect for different layers.
You won't expect it for different layers. That's
I'm
right.
asking all of them.
No, in a conformal field theory, you would expect that, yeah, it's like scale invariant as well. So it's like even in the same layers, they're like even different layers are related by some simple transformation. So in a general thing, so when condensed matter people do this, they don't actually solve for like all things. They'll just like put in the fact that it's the same everywhere. So,
But I mean, okay, I see.
yeah, but here I'm not putting that in, but you could. Yeah, I'm not being very precise about what the choice of the tensors is. I'm just saying there's some tensor network.
But as the central charge becomes larger and larger,
Yeah.
there's a sense in which tensors that you get out of from the vacuum state, the ones that model the vacuum state, that come out of the variational procedure, they become some sort of one thing.
Yeah, that's right. So when that happens, so that's basically what the random tensor network as well does, which is when you have some large bond dimensions, there's some large parameter controlling the bond dimensions. And as long as those tensors are like random enough, like typically when you have a large central charge, like interacting theory, you'll have pretty random like OP coefficients and so on. So what will happen is those effectively will be random matrices of large dimension, and they'll basically behave isometric for that reason. And that's the reason that the area log gets saturated.
And the bond dimension is a proxy for central charge.
So the bond dimension is the size of the Hilbert space here. So the way you should think about it is the log of the bond dimension will be related to A over 4G on the gravity side. And A over 4G is like central charge times some parameter.
I remember early on, Tadashi tried to assign some geometry, some kind of metric configurations. I don't know whether that.
I don't know if that succeeds anywhere beyond like the vacuum and maybe perturbations to the vacuum. In general, I don't know. We don't really know how to reconstruct the geometry from like these simple distance metrics.
But nevertheless, you can think of this, the number of cuts as some kind of measure of an area.
Yes.
In what sense?
This is just, so I'm just saying that if we think about this as a toy model of ADS-CFT, then that's the natural map from one to the other. In the sense that the entropies will be related in that way and so on.
So it's like a definition of area.
Yeah, like I have the freedom to it's like a definition of area over 4G in this theory.
Thanks.
That's right.
I sort of had a, maybe, I'm not sure, related question, and you could probably come to all of this, but say you take one of these random tensor networks, which has got these nice properties in terms of RT formula and so on. I imagine also that bulk reconstruction will work well there.
Yes.
Because you kind of put it in.
Yes.
So now you take two bulk operators, which you reconstruct on the boundary.
Yes.
And they have some correlation in the bulk as a function of distance.
Yes.
Can you reproduce anything like that notion?
You can, but I mean only in principle. Like just as you said, like there's an abstract argument which says that if you have the RT formula plus quantum corrections, then operators in the bulk region can be reconstructed on the boundary side.
Yeah.
And then just because they can, I mean like two-point functions or whatever will be the same on either side. Like will be related on either side. Like you can compute, you can map the bulk operators to some boundary operators whose two-point functions will be the same as the bulk two-point functions. That's an abstract argument. It's not like you can do it explicitly in some example.
Okay, yeah, you should know. I was wondering, I mean, so now that you can do that, then of course the bulk two-point correlator is a physical way of measuring bulk distance.
Yeah.
And are we saying that we get that right in some sense encoded in the boundary?
Only in principle though. Like, I don't know if, in principle, yes. Like for example, this tensor network is kind of like, so in ADS-CFT we have this HKLL map, right? So we can write down, like given the geometry, we can write down operators in the bulk in terms of operators in the boundary, then you can take the two-point function between those and you reproduce the bulk two-point function which knows about the bulk distance. But in that context, like you really started with the bulk geometry itself. So you're sort of putting it in by hand, but it's still non-trivial that it reproduces this. But it's not like you could, at least at this point, I don't think we can start from the boundary state and just write down what it is in the bulk. Like, I don't think we have enough control in general to do that.
Well, in some contexts.
In some context, we can.
You can.
If you have a Euclidean particle state or something in the normal field theory, then you could imagine deriving, what the bulk geometry is, what the state of the quantum fields in the bulk is, and then one expects that the bulk to boundary map is it's an isometry.
Okay, it's an isometry, I agree. But I was wondering if you're going to say that bulk distances are tied to how many bonds you cut or area is tied. Can we then also get a notion of bulk distance in terms of bonds you travel and so on. Then there's a
problem
consistent
here
picture
is
which
that-
is working.
So this model is like a toy in the sense that, so we have these bulk states that we put into these yellow legs, but you can put in whatever state you like. It doesn't have to be anything like the vacuum state, which has some nice correlation functionality. This is like a very discrete model. You can put in something that has zero correlation between two different bulks.
Empirical, there's no notion of a gap, super gravity state.
Yeah.
with
So,
which
so
you
what
could
you're
prove
really saying is if you
distances.
pick like some nice class of states in the bulk, then you should be able to get the distances from that. So this is a little more general than that.
We need
So-
some notion of large central charge.
Not even just that. I think you also need like some particular class of bulk states to be able to say this, like which have nice. Like really, what you mean is that you have, let's say, the vacuum state on the boundary,
Yeah.
and then you have some nice bulk state which maps to that, and then you can maybe do something like
Yeah,
this.
no, but I thought we were
But,
starting with the vacuum
yeah, but-
because the area law is coming.
That's right. But once you add in these bulk states, you've now given yourself more freedom. You can choose states which are in some crazy subspace, which include the vacuum, but maybe they also include some very non-trivial states which have high energy or something. They just have log entanglement, but they could be very different.
Not in this.
Yeah.
So maybe also, but so this, if you're interested in the
The
space
time
of
is
states,
flexible.
I'm like,
if you're interested in the space of states where the entanglement increases with the logarithmically,
yeah,
then this is one possibility of generating those states.
yeah.
Other possibilities would involve networks which may look like that but may have different topologies.
Correct.
Right?
Correct.
Is it that those would access some other part of the Hilbert space, some other subspace?
In general, they would. I mean, firstly, I should say that the tensor network will not even span a subspace, right? I mean, it's not even linear.
Yeah.
So it's going to be some class of states, some subset, and in general, they'll be different but maybe overlapping class of states in what you just said. This is like far from a unique representation.
Right. So one would imagine for Ising model or something like that, if you
Yeah.
want to model it correctly,
Yeah.
then presumably, I mean, you may need that other stuff.
You
also.
may.
From holographic intuition because it's small c. So
Yeah.
vacuum state may not just be that, but
Oh, good. Sorry.
of some
So I
others.
think what you're saying is like you want a network which is isometric and has a geometry. Then maybe you expect something like that, right? I mean, otherwise you could just write down a Mera which encodes the Ising vacuum.
Okay.
It just won't saturate the RT formula.
Which will not saturate the
Yeah.
Okay. I see. Oh, okay. So, okay, fine, I got it.
Sorry, maybe perhaps related, we can even discuss this later. Is there any evidence of something like a diffeomorphism?
There isn't. That's good. So that's part of the issue with this, which is we don't exactly know how to get diff invariance, and more generally just time dependence as well. Like I will talk a little bit about how we can see time dependence in these cases, but roughly it misses that part. But I don't know if maybe that's just we've not gotten there yet. Like there are some models like these double scaled SYK models where it seems like there's a very accurate sense in which the bulk is described by a tensor network, like a superposition of tensor networks, but tensor networks nevertheless. And just from the geometric picture, we know that it should have something like diff invariance. So maybe in that context, like we could start getting to diff invariance. But right now, what I'm talking about is like, I don't know, you just pick some spatial slices and it misses diff invariance.
By the way, there's a lot of time is not that hard and
Yes.
fast.
Yeah, no problem. Yeah. I mean, I knew that, but I didn't know it would be that much. Okay, good. So good. So you get all of these features like subregion duality and the quantum extremal surface formula from these simple models. And the advantage is once you have that, then these models are usually more tractable. There are computations you can do in this. There are many techniques that you can use, which you can then apply to holography if you understand holography, if you can translate appropriately. So if you can translate results from the tensor network side to the holography, to like gravity in general, then you can learn about quantum gravity directly from this because you have much more control in this context. Good. So The star of these set of lectures will be these random tensor networks, which is specifically the toy model that I'll be talking about mostly. Which is, so let's say you're given a graph, let's say this one, which has some set of edges and some set of vertices. Then you can define a boundary state in the following form. You pick a vertex, you pick a hard random state at each vertex. So let's say you pick this vertex. This vertex has 3 legs, so these 3 legs. And you pick a hard random state in the Hilbert space of the product of these 3 points. Okay, so if each of these had like dimension 2, then it would be like picking a random state in dimension 8. Once you do that everywhere, and then you project onto maximally entangled Bell states for each of these edges. So let's say you picked a random state here, you picked a random state here, and then there's an edge connecting them. So you now project down the state, the random state that you picked, with a Bell pair connecting these two. So everything in the graph except the open legs are now contracted. So you're left with a state that lives on these boundary legs, and that's how you're supposed to think of the boundary state. So this is supposed to be some coarse-grained representation of the boundary state. A side comment which I'll maybe talk about a little bit is that here we pick hard random states. Hard random states are often a little notorious, like people don't like them because they're computationally hard to prepare and so on. They don't often, quantum information people, I mean, they're useful as calculational techniques, but in the lab, you can't make like a hard random state. So often what are called K designs, which are some sort of, they look random up till some moment, and then they're not random, will be sufficient for some purposes. Like for example, to get the RT formula, you really only need a 2 design, which is like a very, very simple thing to prepare. In general, like as you start computing finer and finer quantities, then you'll need more amount of randomness. But what I'll work with in these lectures is hard random states.
What are those finer quantities which become better and better with increasing gain?
So for example, in my next lecture, I'll talk a little bit about things like the reflected entropy and entanglement negativity and other like information measures. You can compute these, and you'll see that in order to get something that looks like the gravitational path integral, you need like higher designs.
Sorry, shameful ignorance, but I just want to understand the mathematical structure. So each vertex is a tensor because it is a product of 3 states.
Yeah, how many other legs it has, yeah.
Okay, and then right at the boundary, one of the states goes and hits the boundary.
Yeah.
Okay, and now you choose, so you've chosen a particular tensor?
No, pick any choice of, like, it's like a hard random tensor.
So hard random tensor and hard random states?
No, sorry. So the tensors live at the, I mean, when I say state, I just mean hard random tensor. You can think of that hard random tensor as a state on the Hilbert space of these 3 legs.
I see. Okay, fine. Okay, fine. So this, so far you've specified your choice of tensors.
Yeah.
And you've not told us what state in the Hilbert space will be.
No.
Okay, thank you.
Yeah, yeah. You pick any choice of hard random tensors, it'll give you 1 state on the boundary.
Why will it give you one?
Because everything else is projected down. So you had a lot of open legs, so you could think of it as a state in the Hilbert space, which is the tensor product of all of these vertices. But then you project it down to maximally entangled states. So for example, these 2 share an edge, and so you projected that state down to a maximally entangled state between these 2. So you've projected down all the open legs that you had, except the ones at the boundary. So now you're left with just something that's a state on the boundary.
I see.
That's just contraction of indices.
It's just contraction of indices in a specific way.
I see.
I had sort of my question also, which is, I mean, there's more than one class of the orbit of hard random tensors. Doesn't you start from one and randomize it? You don't get all the other hard random tensors. That is there? You have, of course, many more than one state.
No, but I think the hard, so let's say you pick some vertex, and there's like, let's say 8-dimensional subspace here.
Yes.
Hard random is just like uniformly picking a state in that. So it's picking, it's among the whole possible Hilbert space.
I see. But so maybe, I'm sorry, my question is so dumb, but I start with some vector and I randomize it.
Just like
I started with some other vector and I randomize it. Do I actually end up with different vectors?
no. Well, what do you mean? So you end up with the same
Different
measure,
states.
like it's the same what's the sample space from which you're picking.
I mean, do I end up with a different state? That is, I take T, I, J, K, I, J, K, and now I take T and I randomize it.
Yeah, you'll end up with different states. The state will depend on T.
Where you started, huh?
What do you mean by started?
Okay, so maybe I'm misunderstanding it.
So maybe the way
I thought,
about it,
okay, if I think of T, I, J, K as a vector in some 8-dimensional space. Suppose
but a random one?
Okay, to start with, it's a definite vector.
It's a definite one.
But now I randomize it by doing unitary transformations.
Yeah.
So then I get some, linear superposition of vectors with some weight. That's how I was thinking.
Oh.
Is that wrong?
You could think of it that way. I mean, it's just, maybe it's fine to just think about just picking a random state then. Like instead of thinking of it as a superposition, it's just like one particular state on that orbit that you're picking.
But is it one or is it it's averaged? Oh, I thought
eventually we'll average over it. So let's think of this as like picking one instance of a random state, and that will generate like one instance of a boundary state. When we compute things, like for example, the entropy or anything like that, we'll compute it for each instance and then average at the end. So
the map is really for every
choice of
state.
Yeah.
After projecting to the bell pair,
Yeah.
you get a state in the boundary.
Yeah.
That is the map, huh?
Yes.
Okay. Then I understood.
Actually, I have the same question. So, let's say I have an 8-dimensional space.
Yeah.
Now, the R random stuff would describe, the coadjoint orbit starting from one particular state.
Yes.
But coadjoint orbits foliate the entire 8-dimensional space. So you have to say which coadjoint orbit you are at.
I think normalization of the state may. If you want it to be unit norm, I was thinking.
Sorry,
I see.
So you want some particular guy just integrate for you. So you
that's what I was saying. You integrate over all. I don't think there's like different orbits anymore. Like they all have the same orbit.
Only about the property.
Like it's like a sphere, right? Like so, it's on the block sphere. You're taking and then just integrating over the whole sphere.
Yeah, no, I think at least Shiraz says, I use a non-1 equal to 1 condition.
Yeah.
Then I think it would specify a unique quadrant.
Oh, I see. You meant like different norms. Okay, that's okay. Yeah. That, I agree with that.
Yeah.
So it's like so just pick the set of norm 1 states and then pick a random one.
Yeah, like R3 for example. It's not
R3 will not.
It's not a single quadrant.
Correct.
It's
this is just the
estimate by the radius.
Yeah. It's just the estimate.
But then with non-fixed, you have one coadjoint.
Yes.
Yeah.
That was my point.
Yeah.
These are the states.
Yeah.
And just to make sure I'm understanding that tensor has actually 4 legs because one goes out into the bulk.
So I'm being you could consider that. So for the simplest tensor network we can consider is where these yellow legs are just not there. Then it's just 3 these in the plane black legs. That's all.
That will give you the vacuum state, I suppose.
You can use it to get the vacuum state or whatever state you like. So that's the simplest way in which tensor networks are used, just as a description of the boundary state. But in order to see something like subregion duality or something, you want bulk degrees of freedom. So then you just add in these legs, which will give you a map from the bulk state to the boundary state.
Right. So, but before you put in these yellow, if you actually use 3 index tensors, you'll get a unique state of the boundary.
You'll get a unique state on the boundary.
So in order to get many states on the boundary, you need a 4 index tensor.
That's right. If you want
So then that answers my question, that actually the randomizing gives you a unique state.
Yeah, maybe that's what you mean, but like if you pick a single instance of a random tensors, then you get a single state.
You will, but that's not your ground state.
It depends on the choice of the tensor.
Yeah, but I thought your ground state will have its entropy properties correct after you do the randomizing.
No. Pretty much, this is going to be self-averaging. So pretty much all the states that I have, like each instance is roughly going to have the same entropy properties.
I see. So what is the map then? On the boundary, you have many states which have all the properties.
So for each choice of tensor in the bulk, you'll get one particular state on the boundary. So there's a set of states that you have in the bulk, and there's a set of states on the boundary for each instance. you can take any one of these set and compute the entropy, and you'll find that it satisfies the RT formula to a good probability and accuracy.
Should I think of these as like ground states of various?
Yeah, you can think of it as like changing the Hamiltonian, and then it's like a ground state of some different Hamiltonian.
Large class of
But if you fix a Hamiltonian, then one of these is the ground state and the others are some crazy state.
So you get many different states because you're not actually performing the average. You're saying you're just picking a tensor.
Yeah, I'm always performing the average right at the end. So I want to pick an instance, compute whatever I want to, and then average over.
But if I performed the average, I would get a unique state, right?
Well, I don't know what state,
I mean, a unitary times some fixed tensor integrated over this is a state in the input.
situation happens at the bit. So you compute whatever quantity you want to compute, like a correlation function.
Yeah.
Then you
You're not supposed to compute the average.
there's no average state. I think what does exist is like an average density matrix. So for example, if you take psi, and then you had like u dagger acting on it, and then you integrate over u, then this is just the identity, up to normalization. That's the average density matrix. But there's no average state as such.
Okay. So the averaging is just for convenience or something.
Yeah.
And the idea is that you actually have many states in this system as it stands, which have the properties of the ground state. And you,
in terms of entropy at least.
in terms of entropy at least. And so if you wanted to model a system with a unique ground state, like we would for purposes of holography, then what you're supposed to do is actually choose some fixed value of the tensor, some particular instance.
Yeah, so for example, you would like, if you were a condensed matter theorist, you'd like optimize over them, find which one is your correct ground state.
Okay, optimize over the tensor.
Over those tensors.
Optimize separately over each tensor and each one.
In principle, you do that, but like Abhijit was saying, like if you have a translation invariant system, you can set them to be the same and so on. Like there's some simplifications, but in general, yes.
I see. And what is the size of these tensors going to be?
Yeah, so that's something that I get to choose,
okay.
It's part of the specification of the graph itself. So these edges come with some weights, and the weights are the log of that bond dimension. So I get to specify what they are.
And are you going to, I mean, to get your approximation good, are you going to take them to be very large or finite?
They're going to be very large, yeah.
Okay, fine.
But not like cut-off percent, right?
Not cut. Yeah. So when I say large, it's like so as I was saying before. So the log of the bond dimension maps to a over 4g, and g is going to 0, so it's large in that sense. But a is like finite.
Yeah, I mean like large in the central charge sense.
Large in the central charge sense, not in the UV cutoff sense.
Oh, not in the UV cutoff sense. So for if
I mean, yeah. I guess you can think of it as the bulk UV cutoff, right? I mean, like, yeah, but not in the boundary UV cutoff.
yeah, but I was wondering from the CFT perspective, if you're just optimizing over a 10 cross 10 cross 10 tensor,
Yeah,
then there's no chance you'll get something exactly right.
that's right. That's
The thing that seems to be nice is that you don't need it to be like, if you're at a scale going smaller and smaller. I feel like you don't need to scale the bond dimension.
I mean, at least it has to be, I think it has to be, there's some value it has to be larger than. Like if you have large central charge, then it has to be sufficiently large for that to happen. I
But
think
if the
that's what
total number of parameters in your variational principle is 1,000, there's no chance you'll get exactly right.
Yeah, but if it's 1,000, it's going to be like, I mean, so let's say you have the Ising model, then maybe you could choose each of these to be two-dimensional or something.
Okay.
And then you just specify the number of layers. So you specified some number of layers, then you end up with a lattice theory with some cutoff scale.
Some cutoff scale. And in the end, when you're choosing your state, you will do a variation over some number of parameters.
Yeah, but those number of, like, because if you want to take the continuum limit, you'll make these more and more layers, right? So there's going to be way more.
But you said that each of the tensors was taken to be the same, right?
On each, so what I meant was, I mean, on each layer, they'll be the same just by translation invariance. By scale invariance, they'll be related in some way.
Okay, so then the number of parameters is finite. There's no chance then you get the exact answer.
Increase this as you increase the layers.
No, he said that the same parameters.
No, but
Across the layer they are the same, but as you increase the depth.
No, but he's saying that the tensor here is related to the tensor.
No, but I think that will also be a function of like how many layers you build up. But, I mean, there'll be some sense in which conformal invariance is encoded into it.
But yeah, is it a new parameter or not? What the tensor is at the next level?
I think it's a new parameter.
Okay, fine. Then if you put an infinite number of parameters, good.
Yeah, so in the continuum limit, it'll be an infinite. So like a C-mera will have like an infinite number of parameters.
I just, yeah.
And you have this, you're projecting onto maximally and negative state to get this entropy 2 dB scales, like, so when you cut across, you get long. Is that the
Yeah. That's right. So in a general network, suppose it was a two-dimensional thing, then you would just say that the entropy here is bounded by that cut, which includes that log 2 factor that you just said. So whenever I work with this, what I'll do is take the bond dimensions to be large, and then it'll actually be equal to that log of that bond dimension.
So can you please say if I change the description at some scale, when I change the scale, what exactly changes?
The values of the tensor can change it.
Values of the tensor, but other than that, like a number of vertices or the number.
So we'll just add more and more layers. So here, like we're building it up from inside, let's say. So you should think of this as like a very IR level thing, and then as you go out, it's more UV. So each layer is sort of moving like smaller and smaller in distance scales, and you're adding more and more layers as you want to take the continuum limit of the bound.
By layers, you mean more vertices?
More vertices. I mean, I'm adding the vertices on some layers just to maintain translation.
And there you're saying that if I added more layers now, these are, if it's a CFT, these are related by scale variance to their earlier.
Yeah, I'm not exactly sure about that. I mean, I think there should be some relation, but they are allowed to change once I add a new layer, for example. It's not like it's the same and now I add some new layer. You know, you make a new network and you optimize again. It's not like I choose what I had before and then I just find the new values for the new parameters. So for a different network, they'll have different values for the tensors. If I wanted to find the vacuum state.
Just to say, this already looks different from standard renormalization group because you impose translation invariance not by requiring that the degrees of freedom in each block are the same when you some block, but you require the Hamiltonian to be translation. You have a notion of Hamiltonian, right? Rather than, because requiring the state to be the same is a very drastic thing in field theory, right? Because the
vacuum, if you are finding the vacuum, then that's also translation.
The 0-point fluctuations, mode by mode. See, if you break it out, if you think of a field theory, even a free field theory, right? It's normal modes are decoupled from each other.
Yeah.
And when you look back in position space, you know, the state is hardly the same. There's 0-point fluctuation in each local region.
No, but I mean, the fluctuations have to be the same at all locations, right? Like,
but in a very careful way. I mean, the state is not the same. You know, you have the normal modes, each of which does its own thing, and that gets superposed. So,
no, if confused by that, if you are you saying that the vacuum state will not be translation invariant?
The vacuum state finally is, but the local values of the fields, if you were to probe them in any way, right?
Yeah.
If you were to compute correlation functions and so on, if you brutally truncated the CFT to say that the field had the same value at every location and try to solve that very simplified toy model of quantum mechanics, you get very different properties, right? See, if you take a
not sure why, because like let's say I had a lattice approximation of that quantum field theory.
Yeah.
I mean, the vacuum of that lattice model is also translation invariant.
Is translation invariant, but because of a Hamiltonian, which couples nearest neighbors, each of which fluctuates independently. See, the underlying dynamics is each individual spin fluctuates independently, but is coupled by a Hamiltonian which is translationary invariant, resulting in a state which is translationary.
Yes, okay.
Okay, now suppose I sort of simplified it by saying I'm going to require the spin at each degree, at each location to be the same. That's a very different
expectation.
Yeah, the expectation
is the degree of freedom. The degree of freedom is what is being imposed.
I mean, the degree of freedom is
requiring the expectation value of some operator to be the same at every point or something
No,
more
I
than
thought
that.
here the tensor is made to take the same value.
I think you should think of this tensor more as the analog of the local Hamiltonian. Because you think of this, if I just for a moment, if I give you an analogy, think of the Euclidean particle. Right? The analog of the tensors here are like the infinitesimal Euclidean time evolution that you e to the minus epsilon.
Is that right? You say, think of the Euclidean path integrals building up the radial direction.
Something like that, yeah.
I mean, these degrees of freedom, yeah, they live in the Hilbert space of this. It's like, I mean, even if it was free fields, it would be like the Fock space of the normal nodes.
So you're saying this is more like the Hamiltonian, which couples adjacent degrees of freedom living on the side.
Yeah, roughly. I mean, that's what these legs are doing. Like whenever there's a edge which is going from one side to the other, that's kind of like interaction in that sense.
I see. I see. The degree, I was thinking wrong. You said the degrees of freedom live on the nodes in whatever 8-dimensional or whatever Hilbert space, and this is more like the couplings between them.
Yeah.
I see.
So what, I don't understand what Hamiltonian is coming into the picture.
No,
I maybe trying to compare with the Archie picture.
It seemed to me like a more drastic approximation. I was trying to see whether I was right in that, and perhaps I'm not. Yes. Okay, go on. Thank you.
Okay, good. So eventually, so the gist of all of this is that this bulk geometry is sort of giving you a coarse-grained description of the bulk. So this tensor network is giving you a coarse-grained description of the bulk geometry, which is like a discretized version. But also it's giving you a coarse-grained description of the boundary state, at least in practice. Like when we usually work with this, I don't really care that these tensors reproduce the Hamiltonian of n equals 4, for example. I just want that they belong to the same class of states. Right? I just want most of the calculations that we do will be self-averaging. So pretty much any member of this class of states will have the same entanglement properties or other properties. And so in that sense, we're only ever going to average over these and at least pick those. In principle, you could do the opposite. So this is like a very bottom-up perspective. You could do the opposite where it's like a top-down process similar to what condensed matter people would do. You take a specific CFT, try to write that down in terms of a tensor network. There's been some recent work in terms of that by Tom Hartman and collaborators. You could do that, but that's not what I'm going to do in these lectures. And that's also interesting, but this is from the opposite direction.
So will you also talk about this perfect tensor stuff?
So only in the sense that, let me just say a little bit about perfect tensor. So what a perfect tensor is like if you pick a particular tensor, it's a isometric map from one leg to the other legs, like from the smaller set of legs to the larger set of legs, which is equivalent to saying that the state that you get, if you think about this as a state instead of a map, is maximally entangled across those. So all that you need, so in the happy code, these tensors are very carefully chosen to become perfect tensors. When you have a large bond dimension, the advantage is that automatically comes out. So if you pick random tensors in large bond dimension, they're automatically approximately isometric. So these are already approximately perfect tensors.
Why is it desirable? Why is it desirable property?
That's a desirable property for the following reason. Like if you didn't have this approximately isometric property, there's two things you wouldn't get, which are what we expect from holography. One is the RT formula, because as I was saying, like for tensor networks, you just have a bound on the entropy from the area of this extremal surface in general. It can be lower than that, but the approximate isometry is what gives you the fact that it's saturated. So that's the RT formula. And then otherwise, the other thing is subregion duality, which is closely related, which is because these are approximate isometries, you can represent an operator by just pushing it out using that isometry, and you get some explicit map between these two. But that's it.
And have people computed linear properties using perfect?
I'm going to get to that.
Perfect, using perfect tensors?
Not random tensor networks?
Not random.
I don't think so. I also don't think that it'll give you much like, it'll be much like gravity. It will not be. Roughly because those perfect tensors are like 2 designs or 4 designs or whatever.
Yes.
And higher Renyi entropies will require higher and higher designs.
Yes,
Yeah, I'll say a little bit about that next time.
And sorry, you must go on, but the fact that you projected onto well pair states, I mean, if I had projected onto states which were less than maximally
Yes.
also you might have got some of these.
Very good. Yeah.
So where does that come from?
I will also get to that. That's a very important point. So the first examples that were written down had these maximally entangled well pairs. It gives a very specific property that we find in gravity. You could consider states which have not maximally entangled states, as long as they are still sharply peaked in some sense at large bond dimension. You'll still reproduce properties that are an approximate isometry and so on. The Renyi entropies will look very different, and they won't behave anything like gravity. I'll get to that. But,
so in a sense,
but I here specifically mean the maximally entangled.
I see. So, but it's kind of interesting. You do reproduce behavior more akin to gravity through the bell pair state rather than something less.
In a very specific sense, which I mean, this talk is going to be about how that happens.
Oh, I
Yeah.
see. Okay. Thank you.
So this random state, you mean that it's uncorrelated randomness, right?
No, good. So very
Same
good.
randomness
So
at every point.
So in this case, like what I'm considering is a different randomness at different points. It just makes the calculations a bit easier. You could, like in principle, like if you had something like a actual CFT that you were simulating, then you would expect because of what we discussed earlier, the tensors are the same and so on. So they would be correlated. If they're correlated, the calculations here become more complicated, but you'd still expect similar properties. Those are just more harder to perform.
So you will have many integrals.
So in this case, you should think of them as just all different tensors in general.
I'm really sorry, I'll stop after this, but if you just make some random choice of the tensors all over, in general, you will not produce a translational invariant state.
Yes.
So just some state.
Yes. I mean, the translation invariant state is part of that class of states. What will eventually be the result is that this result is sort of self-averaging. So pretty much all states have the properties that I will tell you about. It's still non-trivial to show that the class of that particular state you said has that property, but I mean, I think you can show that it's just calculationally worse.
And just one last about this.
Yeah.
If I demanded that this state was also, in some sense, both translationally invariant and scale invariant, does that, I think this question has come up before, but does that effectively give you a strong constraint between the tensors?
It would put a strong constraint. I don't know if we know exactly what constraints it puts. In free fields, like it does precisely fix all of them.
Precisely fix all of them?
Yeah. You can write down.
Fine, that sounds satisfying.
Yeah.
Maybe a bit, but the dimension of each leg of the boundary is roughly like n.
You should think of you should think of log of the bond dimension. So it's e to the n. So it's e to the n squared. So it's like log of the bond dimension is like a over 4g, and g is like 1 over n squared. So you should think of log e to the n squared.
And about dimension of this yellow.
The yellow ones are typically picked to be order 1, like it can be whatever 2 or 100, but doesn't scale with n typically. You can take it to be scaling with n, like if you have a black hole system or something like that. But in for pretty much everything that I'll talk about, it's not going to be important. So take it to be order 1. Okay. Stop working.
Pointer's gone.
Yeah.
Maybe if we'll get.
No, it is pointing, but it's not. Click on the slide. I see.
Oh, that's
Wait,
gone too.
even that's gone.
Oh, then it's.
Oh, it's true.
Oh, now it's fine.
Yes.
Yeah, good. That's all. Okay, thanks. Okay, good. So, still background.
You're doing very well, actually.
Okay, good. So why are these random tensors so useful? So the reason it will be is that we'll be able to compute all sorts of different information theory quantities and see how it works and how it's related to gravity. And the way to compute most of these quantities is by using what's called the replica trick. This is basically the tool we have to compute things like entanglement entropy and other quantities like that. And the advantage is the following. So when you pick a hard random tensor, and let's say you pick n copies of it, and average over the density matrix of these hard random states, it's a fact that hard randomness gives you a sum over different elements of the permutation group. So let's take n to be 2, then all that says is that the average density matrix that you get is the identity plus a swap, which are the 2 different permutations you have on 2 elements. And more generally, this is true for arbitrary n. So these gx live in the symmetric group on n elements. So let's say you wanted to compute something like trace rho r to the n. So rho r here is the reduced density matrix on the subregion, and you want to compute the Renyi entropy. So let's say you wanted to, and the simplifications only happen when we take the average. So I'm always going to be taking the average of whatever quantity I want to compute.
But this is what I was asking.
Yeah.
That you are averaging once.
I'll average only at the end.
So that means the core randomness is the same for all of them.
No. This is true at each x. This is true at each
So,
x.
I mean, Vx is some u on some state, let's say.
Let's call it ux because it's not a fixed u.
Yeah.
That's what
ux.
it's ux.
So the average that is being done
Is independent at each point.
is many averages.
There's many averages. This is true for each x.
It's
I
many
thought that
averages.
formula, the first formula is true when you have integral over 1 u.
This is true, and then I'm going to do this independently at all x. Because I picked Vx at all x,
Okay.
and I'm going to average over each of them.
Okay. But what is that tensor n then?
Oh, this tensor n is like at each. So I want to do a replica trick. So I'm building n copies of each x. Yeah, thanks. Was that a question? Okay, good. So let's say you want to compute trace R to the n. What do you do? Well, you can compute it by replica trick. You take n copies and you apply what's called a flip operator. So you apply an operator at capital R, which sort of cyclically permutes the copies so that you get trace rho R to the n. And
Sorry, that first formula I should know, right? I somehow it's not
maybe,
there.
I don't know.
So can you explain that first formula?
Yeah, so the first formula is basically what I was saying here. So it's basically you have some random state and you have some size 0, you have some u factor u, and you're integrating over u. When you have just, let's say, one of these, then as I was saying before, you just get identity.
Okay.
Because that's the thing that is respected by the symmetry. Because it's uniform under the symmetry.
I understand. You
And
use
you
this
take-
thing about clicking of things.
Exactly. Now you take tensor products of many of them. The things that are symmetric are the ones which are like permutation.
Yeah.
Sure, while duality.
Yeah.
Sure world duality. That's right.
Then you integrate
That's
and
right,
then
that's
it makes sense.
Yeah.
That's right.
Thank you.
Okay. So what we did was average at each point. So we have averages at each point, but then there's a contraction. So the legs are being contracted by these edges onto particular maximally entangled states. So what that does in principle, in effect, is at each x you have a degree of freedom gx, which is picking the permutation at that point, right? Because when we did this integration, you had a gx at each point. And then this calculation of trace R to the n just becomes a partition function. It becomes a partition function where the degrees of freedom are gx at each point, with a coupling that is given by the following. So it's like an Ising type partition function where whenever you have an edge, there's a cost which is related to the bond dimension of that particular edge. So log of the bond dimension is like the coupling constant. And the weight is determined by the distance between the two permutations. So if you have a different permutation between two different vertices that are connected by an edge, then there's a cost. This distance function is what's called the Cayley distance. It's basically, if you have two different permutations, how many swaps do you need to go from one to the other? So it's like a very natural measure of distance on this symmetric proof. So you get this partition function, and now when you go to the large D limit, you're basically going to just pick, it's like basically trying to find the ground state of this partition function. So it's like taking beta to infinity. So you're finding the ground state of this thing, and with the particular boundary conditions which were fixed by the fact that we were computing this. So the fact that we were computing this said that we were tracing out trivially on R bar, and we were applying a flip, like a cyclic operator on R. So the boundary conditions are that you apply a cyclic permutation on R, and identity on R bar, and now you just want to find the ground state of this partition of this model, of this spin model, with these boundary conditions. The ground state is pretty simple. It's basically given by two domains. One is identity, one is the cyclic, and they're separated by a domain wall. This domain wall will try to minimize its energy, and so it naturally lands on the minimal surface, which is the RT surface.
So is the quantum mechanical portion of the model useful in this?
Yeah, I don't know if it is. Actually, you could analyze it. I don't know if it has like some gravitational interpretation or anything. No one has actually studied that. I think he means like finite T, let's say.
Sorry, there's two questions. What was dx minus y? It was how far the
So
two bonds are?
dxy, so yeah, so good. So this capital D is the bond dimension. So it's the bond dimension of that specific edge, which you can choose like different for different edges and so on. This little d is the Cayley distance.
Okay, and the cyclic permutation, sorry to be this number on R. So that's just the
cyclic permutation is the thing that gave you
trace rho R
rho R to the end.
Got it. Yeah. Thank you.
Good. So this is what you end up with, and good. So now this trace rho R to the n is related to the Renyi entropy. You can compute the Renyi entropy starting from this, and what you end up with is the following. So it gives you the area of, so the number of edges you cut basically along this minimal surface times log of the bond dimension. The way to interpret this is like the area, this is like 1 over 4g basically. It's like a over 4g.
So the Renyi entropy you're computing is just on the boundary.
Is on the boundary.
And then that surface comes out dynamically.
Yeah.
This the first step that you did was to what it ended up doing was pick a element of the permutation of each.
Exactly.
So I could have just started off with that, just randomly picked an element of the permutation for each vertex, and then did this, then minimized it to the minus n.
As opposed to
picking a tensor and then saying that.
Well, but then the question is like, what are you computing?
It seems like it would give you the same answer. Right?
It will give you the same answer, but so the reason we started with that random state was we were generating something that was like a boundary state, and we wanted to compute the entropy of that state. If you just pick like
but that would be like picking a random tensor just on the boundary. Not for, for all the links inside, it looks like all that did was to pick up some element of the permutation.
But what do you mean by picking G? Are you picking a state at each vertex or no?
No, I'm not picking a state.
This tensor is a thing only when you take n copies. This permutation is a thing only when you take n copies. He wants to do something before you take n copies.
Yeah, good. So that was hidden in the fact that you got this. The fact that you get bell pairs basically says, so you're applying some permutation, right? So you're applying a permutation and taking a trace. If the permutations on either side are different, then there's a cost because of this bell pair. Because the bell pair wants to sort of have both sides be the same, I should say. I mean, I'm being a bit heuristic about it, but that's where it comes in. The small d comes from the fact that you had these bell pairs. If you didn't have bell pairs, like if you had non-maximal entanglement like Sandeep was saying, this d gets changed a little bit.
Log p is the factor is being included.
Well, that as well. Both of them came from that. Yeah.
Whether this is Renyi means that the division by n-1.
There is a 1 over n-1 there. Yeah.
So this is not really trace of rho to the. I mean, you take the log and
so
divide
yeah.
by n-1.
So this trace rho r to the n-1 will give you. So it has an e to the minus this distance. The only distance will come from this surface, right? So that's the distance between the identity and cyclic is n-1 in this Cayley distance. So you get e to the minus n-1 times this factor.
So f already has in it the n-1.
But f ends up being n-1 because of this distance function. Yeah. And then there's a 1 over n-1 log that all goes away, and then you end up with this. So it's very important to note that this is a flat Renyi spectrum. It's n independent. And this would be an important feature. Okay. Okay, so now that we give you an overview of these three lectures. Go on. So good. So today's lecture will be about talking about what are called fixed area states. So everything I told you about random tensor networks right now is going to be things we're going to try to find in gravity. We're going to find analogs of it in terms of these fixed area states. So this duality is what we'll talk about today. Tomorrow, I'd like to talk about some applications of this fact. So once you've related random tensor networks to fixed area states, you can apply it to compute other information theory quantities, and I'll specifically talk about the reflected entropy and entanglement negativity. And then finally, in the last lecture, I'll talk about some work on trying to bridge the gap between tensor networks and gravity. I'll talk about some of the shortcomings of tensor networks and how we can try to fix them. But that's sort of the rough plan. Okay, good. So today, I'll talk about fixed area states to start with. We'll discuss the replica trick and see how it's related to the, you missed the overview.
Middle age, you know, imposes its constraints. I'm sorry. I'm sorry. Go ahead.
No, you missed the least important slide. That's fine. So then we talk about these fixed area states. We talk about the replica trick for these fixed area states, which will be related to the random tensor network calculation. We'll talk about the Lorentzian space-time associated with them, and maybe today or on the last day I'll talk about going beyond these fixed area states. Okay, let's start with fixed area states. So in order to talk about fixed area states, let me contrast them with what I'll call smooth states. So smooth states are basically, I'm defining all of this in terms of the path integral, and all of this goes back to the work of Gibbons and Hawking, who gave us this magical rule, which was all you have to do is compute, given some boundary conditions, just fill in with whatever gravitational saddle solves the equations of motion and is smooth. It solves the equations of motion everywhere, no other boundary conditions, nothing. It has been remarkable in the sense that it's given us the black hole entropy, it's also given us the page curve, and a lot of things come out of just this simple fact. And so smooth states are typically, so for example, let's say you were computing the norm of Permofield double, which is just the partition function, trace of u to the minus beta h. You have a specified length beta on the boundary, which is fixed. That's the boundary condition, and then you want to fill in with some saddle which solves the Einstein equations with that boundary condition. Fixed area states, on the other hand, are a situation where you instead want to apply, so the area is some observable in gravity. The area of the extremal surface is some observable. You want to project onto definite values of that area and just compute the norm of that remaining state. So the way to compute something like this...
Area of what?
Yeah, good. So it's the area of the horizon in this context.
But, so sorry, Pratik.
Yeah.
You should complete, but when you say it's an observable in quantum gravity...
I
Is that
only mean like semi-classical.
Okay, semi-classical.
I only mean semi-classical.
That I agree.
Most of what I'm going to talk about will only be working in the saddle point, maybe one loop approximation and so on.
Yes.
But maybe in situations where we understand the path integral a little bit better, like maybe JT gravity or something, I think we can do this even at the full path integral level. Like you could in principle define all of this.
Define an area.
Wherever the gravitational path integral is well defined. Because the area is just some value in that metric.
Subject to boundary condition.
Subject to, yeah. I mean, yeah, so we're integrating subject to some boundary condition.
Sounds like loop quantum gravity.
We're going to
A joke.
yeah. So, excellent. So, yeah, you see that Don Marolf is heavily involved. So, loop quantum gravity. Although he says he's left that. Okay, so good. So now, when you want to compute something like this, the path integral is still specified by the same boundary conditions with a length beta, which is because we're computing these Thermofield double norm. But then we want to project onto definite values of the area. Now, specifying the area is basically the same as at the classical level for a black hole. It's just the same as specifying the mass, so specifying the energy basically. They're just in one-to-one correspondence. So what you end up with is a solution with a definite value of the area, which solves Einstein equations everywhere else, except it has this extra boundary condition of fixing the area at this point. But you can't do that without, I mean, generically you can't do that without introducing also a conical defect at this point. So that's what so this is an example of what a fixed area state will be like.
It's are we Euclidean or?
This is Euclidean, this is all Euclidean at this point.
So area means, area was just
a codimension 2 area.
Okay.
But just I was going to say, ask you exactly the same thing, that if you were going to do this in gravity, you would have to introduce a conical deficit or something to keep the area fixed in the path.
Yeah, we're going to get to that.
Okay, yeah.
I didn't quite understand this.
Sorry?
This is a one-dimensional CFT.
Oh, this is just a toy picture. You can think about this as a higher dimensional CFT with some beta circle, which is the thermal circle, and this is just like the transverse direction. It's a radial direction.
So what?
Yeah. So the area in this simple example is just the area of the horizon. More generally, it will be the area of the HRT surface, like the extremal surface.
So we want a gravitational state which is an eigenstate of area operator.
So we want so in principle what we're doing is we're defining a state using the path integral, which is roughly an eigenstate of the area operator.
What are not eigenstates? I mean,
What are not eigenstates?
Semi-classical geometry that is.
It's a semi-classical geometry. So in general, a semi-classical state is more like a coherent state. So it's like you have some fluctuation. So one way to see this would be when you compute like 2-point functions or higher point functions, there'll be some non-trivial width that the area has. The width of the area typically scales as square root of g. So it vanishes in the g goes to 0 limit, but it's still there. So it shows up in calculations like the Renyi entropy and things like that.
But also you're going to specify the area independently of the temperature, right?
Yes.
So semi-classically, area will be determined by temperature.
Yeah.
Exactly.
Here he's going to choose them separately. So he's going to do violence to classical general relativity and everything.
But is there a CFT state that you can right?
In some cases you can. So for this simple example, that's what I was going to say. So there's a classical equivalence between these two objects. So at the classical level, the microcanonical thermofield double is basically a fixed area state. This is not true once you start including quantum corrections in the bulk. And so it's often hard to write down an explicit state on the boundary, which will be like fixed area state in the bulk. But that's why defining it directly from the gravitational path integral side.
But what is a microcanonical TFT?
Oh, a microcanonical TFT is just like, normally the TFT is like e to the minus beta E. And this is like over all energy.
Yes.
But now you just want to sum over energy belonging to some E naught to E naught plus delta, some small window.
Even though there is a beta there.
That won't matter. Like in this small window, they're basically all the same. So it's like having the identity here. It's just a number.
I see. I see.
It's like acting with a projector on this subspace on the thermofield double.
I mean, I was going to ask something related to perhaps what Omkar was saying. There is, from the boundary theory perspective, temperature and entropy are conjugate variables.
Yes.
Right? I mean, that's how I would have thought of it. TDS, mu dn, like that. So, of course, it's perfectly fine conceptually to say we want to work at fixed chemical potential or fixed number.
Yeah.
Right? But to say that you want to work at fixed entropy and do a sum, kind of seems, I mean, I don't know what that means. Entropy comes out, you give some constraint, like I want to fix the energy, the number, or fix the temperature in the number. Then you get some number of states contributing, and that log is entropy. But conceptually, I mean, would the partition function make sense if I were to fix the entropy? I'm just asking. To me, it seems. But before we go into gravity and so on, just from the CFT point of view, it seems a bit strange to.
Well, I think what you're doing is like the CFT state has some spectrum, and you're just like picking some window and projecting onto that. The size of this window is determined, like where you project is determined by, I don't know, let's say the energy or some other parameter. But all you're specifying is like where in the spectrum are you projecting onto, like depending on how many states it has. I think that's fine.
I mean, I would understand, if you were picking based on energy or some conserved quantity.
I mean, that's what we usually do.
That's what we usually do.
But there's nothing stopping me.
No, but then how does temperature enter the quantity?
So the temperature is fixing this original spectrum, and then I'm choosing which window to project on.
So all the temperature is doing is giving you your normalization.
Yeah. That's right.
It's just an overall number.
Initial state. It's giving the state I'm going to act on.
But all that it's doing is it's giving you the microcanonical entropy times a number.
Yes, that's right. Yeah. That happens to be the case here.
Okay.
Yeah.
The temperature is giving that.
The temperature is just giving you some envelope around this thing.
Yeah.
So it's just going to give you e to the power minus beta e at that e.
Yes, exactly.
Times the microcanonical entropy.
That's right. That's right. It's basically just a number.
So it's a normalization.
It's normalized.
It's just a normalization in this simple case. Yeah. I mean, yeah. But that's the principle. So you start with some state that you know how to prepare. Like the nice thing about the fixed temperature state was I knew how to do it with the path integral. And then all I'm doing is like projecting that onto a specific window.
Yeah. And from the bulk point of view, as you said, I think this is like having some IR boundary.
If you wanted to specify the energy, then it would be like specifying a UV, like a boundary condition really at the asymptotic boundary, because that's just specifying the energy, that's an asymptotic observable. This is an IR boundary condition because we're specifying the area. Classically, these are the same, but quantum mechanically, they're not, because you can have like excitations outside the horizon, for example, which are captured on the asymptotic boundary, but not here. So the way I think about it is it's like an effective semi-classical description with this IR boundary condition. I mean, I don't expect it to make sense in like full non-perturbative quantum gravity.
Yeah.
Maybe, unless the path integral makes sense.
But just to understand, sorry, in terms of the gravitational path integral, let's say we do it for a fixed temperature.
Yeah.
You will say, I'm going to specify both the temperature and the area independently.
Yeah.
Right, if I'm right. And normally, of course, the area is something which just from the fact that you don't have a conical deficit gets fixed. So here, in general, you'll be forced to have a conical deficit.
Yes.
And you'll define the path integral.
Yes. Yes. Okay. Thank you.
So the answers will not depend on the temperature.
So they will. I mean, here in this simple example, they won't. That's
They'll
it.
depend in a trivial way.
In a trivial
E to the power minus beta, classical.
Yeah. In this simple example, that's right.
Probably observe things, normalization factor, the way they are defined, the normalization will remove the norm.
Yeah. Typically. It won't matter. I mean, basically, the geometry that you get here will be the same as if you just specified the energy anyway, instead of specifying the temperature. So, but that's why I started with this simple example. I mean, this won't be the case always. Okay, good. So the general rule is as follows. So what we do with the gravitational, yeah.
And for the vacuum state also, there is something to be said.
Yeah. I'm going to get to like more general states. So more generally, what we'll be doing is, so whenever you compute some path integral, what we have is we specify some boundary conditions at the asymptotic boundary, and then we integrate over all possible metrics. Like, we don't really understand what this means in general, but let me just write it heuristically anyway, with the action that your theory has. The saddle point approximation obviously tells you to find the solution to Einstein's equations or whatever high derivative theory equations with given boundary conditions at the asymptotic. In this case, in order to fix the area, we're going to add in an extra Lagrange multiplier. So we're going to have the same integral over metrics with the boundary conditions at infinity, but then further we add a Lagrange multiplier mu and add in I mu times A HRT minus A naught, where A HRT is the area of the HRT surface, which is the extremal surface homologous to that region that you care about, and A naught is the value you want to fix it to. Okay, so then clearly the equation of motion of mu sets AHRT equals A naught. That's what mu is doing here. In general, like this is an exact delta function. We don't really need it to be an exact delta function. It can be a Gaussian with small width and so on. I'll get to that. But at this point, just take it to be a delta function.
So suppose I've got a general metric contributing to this path integral.
Yes.
What surface are you computing A of?
It's the extremal surface that's homologous to that region. That's a well-defined.
So when you say extremal, it already has a naught equal to HR.
No, A naught is the value of the area itself. It's not theta. Like extremal just means that the extrinsic curvatures are zero. The value of the area can be, it'll depend on the metric.
Nice.
Right? Like for example, in the black hole example, like all horizons at all different energies will be extremal, but the value of the area will depend on the energy. Right? Does that make sense?
Right.
Sorry, with that will only. Sorry, I didn't quite understand that.
Yeah, so I was just saying, like, take the black hole example. Then AHRT is just a horizon, then all I'm saying is that so let's say you're integrating over like a mini superspace thing where G is just like all the different black hole energies, like just the geometries corresponding. So it's just an integral over dE, and then you have e to the I mu, a as a function, a horizon as a function of e minus a naught. A naught is something I tell you, it's like 2000 or whatever, some fixed thing.
So I understand the notation here. So the boundary condition at the boundary of the manifold is going to be what?
It depends on the state you're preparing. So for example, in this case, the boundary condition was just the length, which was theta. In a general case,
here your boundary, you mean at the
at the asymptotic boundary. That's right. So whatever you like, which you were preparing with some asymptotic boundary condition, all I'm saying is you just modify that with this extra thing. Those boundary conditions stay the same.
Okay. So that part is whatever is you
were working with.
And the only additional thing is you have the integral over.
Now you have the integral over. Good. So now we have again, like we can work with the saddle point approximation. You'll basically be solving Einstein's equations with the given boundary conditions, but now you have this extra source term. So let's discuss what the source term really is doing. So in general, the source term has two parts. So when you vary the area at the HRT surface, there's one contribution which comes from the variation of the metric itself. The variation of the metric while fixing, I'm just using the chain rule here. So just fixing the location of the surface to be at the HRT surface. If you just take the variation, you just get a codimension to cosmic brane. So when you take the variation of that area term, it will just be like a volume integral over gamma, which is just like the tension. With tension I mu, essentially. And there's a second term which comes from the variation of the location of the surface, which is basically d mu a times the variation of the location of the surface as a function of the metric. This is 0 because d mu a is 0. So we started with extremal surfaces, which tells you that this term just drops out. This is sort of where extremality becomes important. Like in general, you could have had other gauge invariant specifications. You could have specified some area of a surface which is, I don't know, trace k squared equals 0, or it's like rest to the boundary, you walk in 10 steps from the boundary or something. You could have done that, but they're more complicated sources in general. Although even all of those things, I think, should be defined pretty well at the semi-classical level using the gravitational path integral and so on. They're just more complicated to work with. But here, because of extremality, all we're left with is this one source term, which is just a codimension to cosmic brane at the HRT surface. Okay. So that was what was sourcing. So cosmic brane, we know source is a conical defect, and that's sort of consistent with what we had in the microcanonical example, where we just have a conical defect sitting at the extremal surface, not necessarily horizon.
Yes, extremal surface is not minimal.
Is not?
Minimal.
In this case, it is minimal, like you can have it not minimal, so there'll be contributions from non-minimal surfaces. I'll talk about that a little bit later. For now, let's just keep it to be minimal. But in general, they need not be minimal. Like there'll be non-perturbative contributions from non-minimal surfaces.
I'm a bit surprised that A naught hardly makes a difference.
It will make a difference. It will make a difference. When you actually solve, so this is what happens. So the solutions have this cosmic brane, so they'll have a conical defect. So now you have two things. So you have the value of A naught is fixed here, and the asymptotic boundary conditions are fixed here. So both the value of A naught will also affect the solution, and the solution will be such that it solves Einstein equations everywhere in this yellow part, and it has some opening angle 2 pi m, which is not generally 2 pi because of this conical defect. And mu's job is to source that. So the saddle point value of mu will be some minus I mu e, so it's some Euclidean conical defect. That conical defect will be fixed by the value of A naught. So the opening angle, so the opening angle 2 pi m will be in 1-to-1 correspondence with the value of A naught that you fixed. If you change A naught in general to solve the equations of motion consistent with the boundary conditions, you'll also have to change the value of the conical defect. So mu will change to accommodate for that. So everything in the end depends on that value of A naught that is specified.
When does it go to 2 pi?
So for example, here, it would go to 2 pi if you picked the energy that was the peak of the energy of that temperature. So it's basically like what we usually do in thermodynamics, where it's microcanonical and canonical, but at the peak of the spectrum. So it's on this point.
But my worry is just from the bulk integral point of view.
Yeah.
You introduce this conical deficit.
Yeah.
And you do a semi-classical calculation, right?
Yeah.
Saddle point gravitation. But the one loop determinants and so on may go haywire there. So your semi-classical.
Oh, good. Yeah, I will get to that.
Self-consistent.
I
mean, the
okay.
gravitational stress tensor
let me say what
will do bad things there, right? I might imagine.
That's true. This is true, and you have to be careful about it. It makes sense as long as you have a bulk UV cutoff. So all of this makes sense in the sense that you fix a bulk UV cutoff, then all of those divergences are fixed by that. So there's some renormalization, and with the given UV cutoff, all of this makes sense. When you remove the UV cutoff, these conical defect spacetimes are singular, and then the one loop determinant will have these issues of divergences and so on. Where, I mean, yeah, then it's not consistent. But all of this is only when you're fixing a particular value of the UV cutoff.
You see, but then you should work. But the answer will depend on your cutoff.
It will depend on the cutoff. Yes. Yeah. So a lot of what I'm going to say will be at the classical level. You can include like one loop corrections and stuff. In general, the one loop corrections will then depend on your cutoff. So you get an answer depending on what the cutoff is. And that's something that we should expect because area on its own is not really a well-defined, A over 4G is not a well-defined thing that's renormalization invariant, right? We know that the generalized entropy, which is A over 4G plus the bulk entropy is what's renormalization invariant. And so fixing something like that would have been, that's like fixing the energy and that's like defined at all scales, so that's fine. But when you're saying fix the area, you really mean, you have to tell me what the renormalization scale is to even make sense of that statement.
I see. So more generally, these things are specified by fixing the generalized entropy.
Yeah, I don't know how to exactly do that because
that seems to be the natural conclusion of what that's what
yeah. You can do this thing where good. So you can do this thing where you can prepare a state on the boundary, look at the modular Hamiltonian. The modular Hamiltonian will have some distribution of this form, and you just project onto something. That projection is morally like projecting onto the generalized entropy, but I don't know of a bulk way of seeing this. Like once you start including quantum corrections and you're just looking at this.
Just at the level of the path integral. At
the level of the path integral, I mean, the problem is then the source is more complicated. Like I don't know what the if you put into the path integral, if you put in like instead of AHRT, you put in like SGen, then it's some non-local source, and I'm not exactly sure what it does. So we don't know exactly what it does, but you could do that. And in principle, it's defined on the boundary, but we don't have a good bulk description.
Well, you should go on, but on the boundary, you take the modular Hamiltonian corresponding to that region.
Yeah.
But now instead of specifying the energy of that Hamiltonian, you specify something else.
No, so normally what we do is just you should think of the modular Hamiltonian as like this. E to the minus beta E gets replaced by e to the minus beta whatever k, right? Like the modular Hamiltonian. Yeah. So it's giving you some distribution, and then you're just choosing which window of the modular Hamiltonian to project on. So it's like picking some bands of
eigenvalues or something.
Eigenvalues, I guess, is the analog of energy.
Of that modular Hamiltonian.
Yeah.
Okay. Go ahead.
Is it just to understand the bulk description of the fact that you're imposing some IR tolerance seems to suggest to me that at least shallow one-sided correlations will not change too much, but two-sided correlations will be something.
Two-sided correlations will definitely, that's right. So let's say you fix a UV cutoff scale, then the area operator is something that commutes with everything inside the entanglement wedge, just because it's space-like separated.
Right.
And so it when you do this, it doesn't. Well, it's still.
I thought it changed the geometry.
It does change the geometry. So in that sense, like it's back reacting strongly.
I see.
It's a Euclidean source. It's not a flow. Like if you had to do e to the IA or something like that, then it wouldn't affect it. But this is like projecting onto a different band of eigenvalues. So.
I was just thinking that it would back react very strongly on the two-sided correlation.
It definitely does that. But in Euclidean, you can. There's no sense in which everything gets affected.
Sure. Okay. Fair.
So, so yeah, so essentially you're left with these conical defect spacetimes. I'll just briefly mention, so the form that the metric takes in these conical spacetimes is the following. There's some complex coordinates you can write down for these normal directions, z and z bar. And then there's some transverse metric, hij, and other components. The components in the metric have what's known as a triple expansion. It takes this expansion of this following form, depending on what m is. Essentially, a special case of these conical solutions is the one where m is 1 over n, where n is the replica number, right? So when you do the replica trick, like Luckwitz-Mardasena, you take n copies and then orbifold by it. So you end up with conical defects of size 2 pi over n. And there, just using Cn replica symmetry, you end up with a form of the metric which is the following.
A0 also depends on n.
A0 depends on n, yeah. I mean, that's what this fact says, which is that there's a one-to-one correspondence between 2 pi m and A0. So n is n. So you get this form of the metric, and the Luckwitz-Mardasena trick, again, you can use and just compute the variation of the action under changing m. So if you look at the on-shell solutions and different values of m, you can look at the variation of the action. This im tilde just emphasizes that you don't pick up any extra contributions from the defect itself. You just compute the action everywhere outside, which is what Luckwitz and Mardasena taught us to do. And you just get minus a over 4g. So this is like some generalization of the Luckwitz-Mardasena tricks at finite values of.
So they had this argument where they added in, subtracted.
Yeah, you can.
It was on shell. That all
exactly. You just do all of that, make to ensure that it's a local contribution from that point.
Okay.
And,
okay.
And you get this.
Sorry, just to understand.
Yeah.
You now in this case you change the boundary, the asymptotic boundary condition to beta like.
No. So in this case, it's different. In this case, all you're doing is changing the local opening angle. So what you're doing is specifying some asymptotic boundary conditions and saying, give me a solution which has conical defect opening angle 2 pi m.
Sorry, and is m an integer or just anything?
M can be anything.
So maybe one should call it m.
Should call it what?
Should not call it m.
Oh. You should blame G and Don for that. It's not my fault. Maybe phi or something really. Yeah. Sorry, yeah, you were.
I was so in the replica trick.
So what we were doing so far was fixing the value of a.
Right.
But because there's a one-to-one correspondence between a and m, you could also consider the path integral where you fix m and asymptotic boundary conditions.
I see.
That's also a well-defined variational principle and so on. You compute the action everywhere outside the defect and look at the variation in the on-shell action. This is basically what we do in Luckwitz-Mardasena. So except that m is 1 over n and we think of it in terms of changing the boundary and so on. But after doing the orbifold, this is exactly what we do.
Sorry, so finally your result was that this action, this variation with respect to this opening angle was a by 4g. And that's something you expected as, sorry, why?
This was expected. I mean, and this is a side fact. This is like, this is just telling you. So Luckwitz and Mardasena basically did this at m equals 1. This is like a generalization of that to arbitrary m. It's like if you, so G Dong had computed this thing that we call the refined Renyi entropy, which is like it's like a Renyi entropy. And that Renyi entropy also has this area law. And this is basically just that fact.
This is somehow the statement that derivative of free energy with respect to temperature is
yeah, that's right. That's right. That's right. You should think of it that way.
Okay.
That's right.
That's why I was thinking.
But one useful thing that comes out of this is that, I mean, this is basically making it explicit how there's a one-to-one correspondence between values of m and values of a. They're basically the slope with respect to m is a. So they're basically related by Legendre transform. As you're saying. Okay, good. So I don't know if I want to talk about this. How flexible are we?
So you can go on to like 1 month if you want, but since there are 2 more lectures to go, if there's a natural stopping point, you should feel free to.
Okay, so good. I'm not going to mention the higher derivative corrections at this point. Well, I'll just say briefly. So when you include higher derivative corrections,
maybe before that, what was the final result of what did you compute that that you wanted to know the answer to?
Oh, I haven't got to that yet.
Okay, fine.
For that area of
Yeah, I haven't got to the. What I'm eventually going to tell you is that these fixed area states are going to be related to random tensor networks, but I haven't gotten to that part.
The area, etc., depends on M, right?
The area, this is a function of M, yeah. It's area evaluated in the solution corresponding to M.
Yeah. So no, I mean, maybe just anticipating, maybe you'll say some, you will explain this, but then the answers will depend on M, but your random tensor stuff was blank.
That's right. And for a good reason, yeah. Yeah. Excellent. So just briefly, when you include higher derivative corrections, it's well known from work by Dong and others that A over 4G gets promoted to the what's called the geometric entropy. It includes the walled entropy, but there's also these higher extrinsic curvature corrections and so on. I'll just briefly say some words about it. You can do the whole story that I said so far. So instead of fixed area states, you can consider fixed geometric entropy states. And the trick is to always consider first fixing M. So you first look for conical defect solutions with the same boundary conditions and so on. But in higher derivative theories, they still have some expansion, but there are more singular terms. So if you look at the previous expansion that we had, yeah. So here you can see that there's no singular terms as you go to z equals 0. But in higher derivative theories, there are some singular terms that show up as you go to z equals 0 in order to solve the equations of motion, which is all fine. You can still, as was shown in this paper, you can evaluate the geometric entropy by, so you define the action similar, you don't include contributions from the defect itself, you sort of make a cutoff, include the action everywhere outside, you need to add some counter terms and so on, but after that, the geometric entropy is well defined and it's basically given by the same thing. It's what you said before, they're related by Legendre transform, so dIm tilde over dm is minus sigma. This is the analog of what we had in Einstein gravity, where this was A over 4G. Once you have that, then you can just define fixed geometric entropy states by similarly just Legendre transforming. So you know how they're related. We know the action in this in terms of this Im tilde, and then we can just transform from one to the other. So higher derivative theories can also be accommodated in the same sense.
Very simply.
Very simply.
Sorry, there's one remedial question, since unlike a lot of the audience and you, I don't think about higher derivative gravity, which is the RT surface to begin with still an extremal surface?
It's
in
not.
terms of extrinsic curvature?
It's not. So,
and so there were some nice simplifications your discussion had,
Yeah.
because to begin with you had
Yeah.
zero order extreme.
yeah.
And despite the fact that you don't have those, this goes through.
Yeah, good. So Einstein gravity has this advantage, which is that you can, as you were saying before, Lupitz and Madisena did this trick where they added in a source term and then they removed it and so on. The nice thing about Einstein gravity is that a well-defined distributional source generates a conical defect. For higher derivative gravity, because of these singular terms, there's no nice similar thing that you have. So you cannot actually compute the action at that location. Like for example, there's a delta function in the Ricci scalar at a conical defect. And so these wall terms can have like r squared, r cubed or whatever. So there's going to be higher powers of delta function. So it's not a well-defined thing. So this, in Einstein gravity, this was something we could do, but we could also do the other thing where we added the source. You could do both. In high derivative gravity, you don't have the luxury of doing both. This is the only way in which you can define the geometric entropy. But once you think of the story this way, it works the same in both cases. Okay, thank you. Good. Good. So now let me tell you about why fixed area states were related to random tensor networks. And the answer is pretty simple. So let's say you were computing trace rho to the n again for a fixed area state. Okay. What's the rules for this? So trace rho to the n has some boundary conditions. So trace rho itself has some boundary conditions. Now you replicate about those boundary conditions. You get some trace rho to the n path integral, and now you want to solve Einstein's equations with those boundary conditions. Typically, when we do this, as Abhijit was saying before, the area itself is a function of n, right? Because the solution changes and so on. The simplification in these fixed area states is the following. So in this case, remember that the boundary conditions were fixed at asymptotic infinity and at the location of the extremal surface itself. So what you're now looking for is a solution which solves Einstein equations subject to asymptotic boundary conditions plus the value of the extremal surface area being equal to A naught. And so it's pretty straightforward to then see that just gluing together original, like if you had like the original saddle, just cut it open and glue it together cyclically. That solves Einstein equations everywhere in the yellow region, and it has the right value of the area. So this has to be the solution which gives you trace root at the end.
Please say that again.
So this was the original solution. So where this was identified with this, so that's the thing that was computing trace of rho. Now just cut that open and glue it cyclically. So glue it in this fashion.
Right.
It's the same. I mean, the background is roughly the same, except the size of the conical defect has changed. But you have the freedom. Mu can adjust itself such that A naught has to be the same, and A naught is the same. So
A naught is the same because it's the same location.
It's the same solution. It's the same location.
And you're going to divide by m.
Yeah, the normalization works out fine. Yeah.
Sorry, A naught is the same because the point at the origin is present in the same for all the sheets.
It's present in all sheets, and it is the extremal surface.
And it is this. So you don't have to do anything.
You don't have to do anything more. So
unlike, let's say, in the vacuum state, where
exactly.
you have to solve the equations again.
Precisely. So if you look at the vacuum state, when you have to do this, it's actually a very hard problem to solve for the Renyi geometry, because you have to account for this back reaction, and that's the simplification the RT formula gives you. You just evaluate something on the original background. That's something you don't have for the Renyi entropies. But for the fixed area states, you do, and because of this reason. And so you just end up evaluating the area on the original geometry, because the replica geometry is just many copies of the original geometry. That's the sense, and so then obviously you just end up with the Renyi entropy being A naught over 4G, and this is exactly what the random tensor network gives you. So the random tensor network also had this flat Renyi spectrum, which you might find surprising from, say, the vacuum state or any other state that you care about. Although like the microcanonical black hole also has this property, like it also has a flat spectrum. But more generally, these fixed area states will give you this flat spectrum.
I mean, this is in the spirit of this first replica that was done, right?
This is exactly in the spirit of so there what we did was firstly what we did was take many copies of the tensor network.
No, I mean, before liquids Manasina, there was a...
Oh, good. Yeah, this is precisely a reinterpretation of Fursayer. Yeah. Yeah.
Making sense of what
this is making sense of Fursayer. Yeah, that's right.
You know, I want just to go back to your microcanonical black hole statement. So yeah, I found it very strange when you flashed that formula for the random tensor network, and it was this flat spectrum, right?
Yeah.
But you say if I take the black hole for fixed energy, and I compute trace rho to the n, you will get the same.
It's just because it's proportional to the identity. Like the state is just, the density matrix is just identity up to some normalization.
It's that picture, right? It's that little band.
Picture.
You're
All
just
of the
taking that little
eigenvalues
band, so it doesn't matter where you were. And it's like it's microcanonical also.
So all of the eigenvalues are roughly the same.
Oh, the band size is fixed.
It's very small.
Yeah, exactly. So it's roughly the identity on something divided by some dimension, and the Renyi entropy is just low.
So I understand that in the in this boundary theory, whatever perspective.
Yeah.
But I meant if I were to do a bulk calculation.
The bulk calculation is also the same. The way it works is slightly different. So the fixed area calculation was this will work more generally. In the thermofield double case, like you can consider the microcanonical, and what you're doing there is you're looking for, so you have some boundary conditions, which is the length, but then, so instead of fixing the length, you're now fixing the energy, right? So when you do the replication, you just end up with the same saddle that you started with. Because the only solution which has the same energy is that particular black hole energy.
With the right power or whatever in front.
Yeah, with some normalization.
That's not the same as this. Right?
That's not the same as this, because there, I mean, I'll get to the connection between those two in a little bit. But they basically give the same answer. There are two different ways of getting the same answer. At the classical level, fixing the energy and fixing the area is the same, and so you have to get the same answer from both, and one is basically a piece of the other, like they're very closely related.
You're going to explain that there's a reason why we should think of random tensor networks as fixed areas.
Yeah. Well, this story is not as general. Like, I don't know in general what the analog of microcanonical would be in a bulk picture. Like in this case, we know that we fix just the energy, and that's the right thing to do. More generally, I guess, like you fix the modular, like some band of the modular Hamiltonian, but it need not have some nice bulk picture. This has a bulk picture, has a nice bulk picture, at least at the classical level, and it still gives you what you need.
So the difference between Lucas-Malus is you add extra boundary condition at the extremal.
This has an extra boundary condition compared to
and that
Lucas-Malus.
removes the independence.
That removes the independence. That's right.
Okay, sorry to be so dramatic, but I mean, in general, if I were to do the fixed energy states and I compute trace rho square and root b, and for some fixed energy,
Yeah.
it'll depend on the energy, right?
For a non-fixed area state, yeah.
Yeah, so why
For,
is
for
it-
the vacuum state. or something.
Yeah, or just, so in the boundary theory,
Yeah.
I wouldn't expect in the microcanonical ensemble that.
If you just have a width, the number of states you're taking is a million.
Yeah.
Then it doesn't depend on it.
Yeah. That's true.
But is that, I thought you said if you do the calculation where you keep the energy fixed.
Yeah.
Energy fixed with some window.
With some window.
Let's say the size of that window is not changing as you change the energy. Then it matters not at all. Right? It's just identity in that size.
But there's some assumption about the density of states in the vicinity of.
Okay, so this width is like much smaller.
Smaller
I mean,
than that,
it's larger than like e to the minus s or whatever, but it's like parametrically smaller than
There are enough states to fill it in.
enough states.
Yeah.
And that's the case when you have a gravity to it or something.
Yeah.
That's okay.
Yeah.
So in this case now, area is fixed and the mu, the quantity.
Yeah. Mu was always allowed to fluctuate because we were integrating over values of mu. It just had to be what was the right thing to give you the area you care about. So it will change.
But in Lucas-Malus, I suppose that was.
There is no mu in Lucas-Malus-Sena, right? Like mu was meant to just fix the area. In Lucas-Malus-Sena, there's no other boundary condition we impose, so there's no mu. Good. So now there are. This was a simple situation where there was just one extremal surface, which was related to a previous question. That was the only surface, which was the minimal surface. But there's more general things that you get out of this, which is, let's say you have multiple extremal surfaces. So let's look at one of these pieces. So instead of this one Pac-Man geometry.
So if you don't mind,
Yeah.
in the simple case, what was the conclusion mission?
The conclusion from here was that a fixed area state is precisely a random tensor network-like state, which has a flat Renyi spectrum, and for good and the replica trick itself is exactly the same as what you did in the random tensor network case. So in the random tensor network case, you took many copies of a tensor network which doesn't back react, right? Nothing changes about the geometry, and all you chose was how to glue them together. This is all we did here. Like all we choose was how to glue it in. So there's a one-to-one correspondence between the path integral and the replica trick for random tensor networks.
And sorry, I think you answered one card before, but I didn't get it.
Yeah.
So suppose we wrote down a random tensor network for a finite temperature ensemble.
Okay.
Okay. Now there, I don't expect that to be a fixed area state. Right?
Yeah, and a random tensor network will not approximate that state well. So okay, good. So this is where I go to like a previous question that you had asked, which was about the Renyi entropies.
Yes.
So the microcanonical ensemble and the canonical ensemble are very close states. So in that sense, the state is approximated well. But what the random tensor network will give you is really the microcanonical state. But the Renyi entropies are very discontinuous when you just truncate some tails of the spectrum. So the Renyi entropies will be flat, and it won't look like the canonical ensemble.
So are we concluding that a random tensor network does not have the ability to correctly reproduce the density matrix of finite temperature?
It depends on what you mean by correctly reproduce. So it correctly reproduces the density matrix in the following sense. Usually what people care about when it reproduces a particular state is that, so let's say you have the actual holographic density matrix and the RTN density matrix. Usually what a good measure of whether it's correctly reproduced is the one norm distance, and you want this to be less than or equal to some epsilon. Okay. This guarantees, so if this is true, then it guarantees that the entanglement entropy is also smaller than some epsilon prime. It also guarantees that the expectation values of operators in these states will also be small, but it does not guarantee that there are any entropies.
So are you saying that it might get averages right, but can't get fluctuations right?
I don't know if I would say that because it's
Because you're saying it's basically taking you to the microcanonical answer, right? So it's just at that energy. Fluctuations start exploring neighboring energies.
Yeah, you can say that. You can say that. There's a close relation between. So it is related to Sandeep's earlier question, which was when we picked in the random tensor network to project onto maximally entangled states. That was sort of what got rid of the fluctuations in the area. It was a choice. And so the tensor network with that choice cannot reproduce these fluctuations in the area. So we got rid of that. Maybe that's one way to say it.
Okay, so right. So it sounds like at best it can reproduce the classical limit.
Yes.
Okay, fine.
Yes. I mean, it can. It can reproduce the one loop corrections of these states. I mean, it can't reproduce the ones for the states that you said, but fine. Yeah.
I mean, to put it another way, let me ask you, Bo. You know, the fluctuations in energy at fixed temperature, or of temperature at fixed energy, are down in the specific heat, right? Which has an N in it.
Yeah.
And so, perhaps for leading order in N correlators, one might hope you can.
Exactly.
Yeah.
That's the classical limit, basically.
Classical. Yeah. Okay, that's what you were saying.
Yeah.
Sorry.
No.
So leading order in N,
Yeah,
the
yeah.
saddle point.
Yeah. So it depends on which states we care about. Like if you cared about these are also like states that you could write down in the CFT, and these states you can reproduce it to higher orders in 1 over n, for example. It's just that the states you cared about was not what it can reproduce.
Yes. Yes.
Maybe related, I don't know, but if you looked at the L2 node, the coordinate node,
For the state,
yeah, could you have proved this?
so the L2 norm is not strong enough to do this. Like you can have states which are close in L2 norm, but they have like very different entropies.
Presumably they will get to see the fluctuation.
They get to see the fluctuation, but exactly. This is typically like the one norm distance is typically what like information theorists would go for. Like that's something that guarantees you. What's the definition of this? The one norm is defined as the one.
Probably just the trace.
Sorry.
Probably not just the trace, right?
It's related to the trace. It's like so the one norm of A is like trace of square root A diagonal. It's the fidelity is related to the 2 norm, I think. There's a bound. So I mean, there's like dimension dependent bounds, which the fidelity is related to the fixed distance. Okay.
Just one thing, I don't know if you've discussed this, but allowing area to fluctuate, can you make that possible by considering the bond dimension to be not fixed?
Yeah, good. So that's related to Sandeep's question. So one thing you can do is instead of projecting onto maximally entangled legs, you can project onto non-maximally entangled legs, right? That would give you fluctuating areas in the sense that you said. But it's still not quite gravity for the following reason. Like if I go back to the tensor network picture, then what you can do is, so you'll get some fluctuations on these legs. But now let's say you want to compute the 2 interval Renyi entropy. Okay, so you compute the Renyi entropy between some 2 intervals of that form. In gravity, what happens is you get cosmic branes that are at both locations, and one of them back reacts on the other. So the area of one of them changes because of the back reaction of the other one. That's something that this model will, even if you add non-maximal legs or whatever, it cannot. Basically, it's the constraint equation that you're missing. Like you want something that tells you that if you change the area at one place, it should change the area at another place. That's something that even fixing it with that doesn't improve.
What if you make the dxy depend on x and y?
Dxy can depend on x and y. That's fine. It still doesn't fix that. That will just change where the location of the surface is and so on. But given a particular network, you're like, given, I mean, you're saying that the state is defined by a network with particular xy, so dxy.
So, Pratik,
Yeah.
gravitational path integral for the fixed area state
Yeah.
can be now related to the gravitational path integral for the non-fixed area state by doing an integral over A naught.
Yeah, you can, but that's only when you have one area integral. So if you had just this one area integral, so now you can see where the non-trivial area spectrum, like non-trivial Renyi spectrum comes from. All you have to do is break a state. So so the fixed area states provide a basis. It provides a basis for you to write other states in. So you can write your favorite state in terms of a sum over A naught, psi A naught, right, with some coefficients.
This is the thing that I wasn't really sure about. I could see that the level of overlaps, but
Yeah.
like this would have, when I compute the overlaps with this, I'll have two sums over.
Yeah, that's right. So there's some, there is a little more careful argument that you can do. In the end, what ends up happening is that the entropy behaves linear in the sense that the entropy of rho will be given by, will be approximately given by sum over these mod squared s of mod ci squared s of y. This is what ends up happening. This is only approximately true though. And you can show this, there are like bounds you can put. It's discussed in a paper by Akers and Pennington. But this is something that you can show. So those off-diagonal terms don't end up mattering. This is not very not generally true. Okay, good. So fine. So this fact that the fixed area path integral is related to the random tensor networks is more generally true. You can have multiple extremal surfaces, and this is sort of where the use of these tensor networks comes in a lot. So let's say, so instead of this Pac-Man geometry, let's say you have one of these pentagon-like geometries. So this pentagon represents, this is the asymptotic boundary, and then you have multiple extremal surfaces. So there's one extremal surface here, and there's one extremal surface here. And this one is just the bra. Like, so there's one extremal surface in the ket, it's two in the bra. So there's basically these two, if you look at any one half of it, there are two extremal surfaces. So if you look at a Cauchy slice, there are two of these extremal surfaces. And this is a generic situation, right? Like a lot of examples will have two extremal surfaces. And so now, if you wanted to compute trace rho to the n, you now have, so you fix the outer boundary conditions, and then you're left with some choices. You're left with choices on how to glue these things together. All of these will satisfy the right boundary conditions for your replica trait, right? All of them, all they need to do is they have to have the right values of the area at the two different surfaces. You've just specified those. And that's guaranteed for any permutation in which you glue them. So you're allowed to apply any different permutation which glues them in some different way. Each of those is a saddle for this same problem. And that's precisely what the tensor network was doing, right? So the tensor network was a sum over permutations applied. Those permutations really here are just the gluings. There are different gluings of this path integral, and there's a one-to-one correspondence between them.
Can you give us one example where multiple...
This is the example, so it's a little hard to draw. Oh, you mean like where there are multiple extra... Oh, you can consider like two intervals in vacuums, and then there's like these two surfaces, and...
Wherever you can
extend your ground. There are two opening angles because you are fixing area in two places.
Yeah, so I'm fixing the area at this surface and this surface.
So normally the leading behavior in G Newton going to 0 is one of them.
Is one of them. The others will give you like some non-perturbative corrections. So typically when you did Lukowitz-Maldacena, you just keep the leading one.
Correct.
But the non-minimal one can, like the non-perturbative correction coming from it can be included. And it becomes important near, say, entanglement phase transitions. So the calculations in this context have been done, and you can see, like, it basically takes you beyond the RT formula. You can see what the entropy is even near the phase transition.
So now, in your path integral, you're specifying the area of which of these extremes? Both.
Yeah.
Both this and the dotted one?
Yes.
And the dotted one?
Yes.
Okay.
Yes. At both the extremes.
Okay. So you're specifying 4 areas.
Really what I'm specifying is the sum of these two plus the sum of these two.
I see.
In the context where there's a maximal surface in the G.
Yeah, there is actually a maximal surface even here. There is a maximal surface which is this X. And that's an interesting question. This is something that's still it's still something that we don't understand. So this maximal surface is what's important for this Python's lunch story, where this maximal surface is important for computing the complexity of reconstructing operators. There's this recent work by Witten and Pennington and Venn, where they showed that using this type 2 von Neumann algebra story, you actually get negative contributions to the Renyi entropy from these maximal surfaces. So you get positive contributions from the minimal and non-minimal surfaces, and you get a negative contribution from this maximal surface. This is kind of sensible because, like, let's say you had, there'll be situations where you create like a extra, where one extremal surface splits into two, and that will generate like a maximal surface. But you want that when you take away that perturbation, it should just become one. So it should be 1 + 1 - 1 or something like that. So roughly, we understand that there should be some contribution like that, but I don't think there's a path integral understanding of where this negative contribution comes from. So there are these, there's this sub-leading Weingarten story by Douglas Stanford and Zhenbin Yang, where they found similar like negative contributions from other like chaos modes and stuff for the 4-point function, for the OTA. But similarly for the entropy as well, I think there should be some of these negative contributions, but this is not something that we understand directly from the path integral. On the tensor network side, there is a small tweak you can do to the tensor network, which is just take the random states and instead of having random states, you have like random unitaries. So as Abhijit was asking before, like when you pick random states with large bond dimension, they end up being approximate perfect tensors anyway. But you can put in the fact that they're perfect to start with, right? So you can say that I'm only going to integrate over things which are exact isometries. And then you do get these negative like Weingarten contributions. So there's something of that form. But I don't know how to see this from the path integral at this point. But there's some hints that there are contributions from those surfaces. Yeah. Okay. So this is where the advantage comes from. So the advantage is that now we know how to map certain gravity calculations to tensor network calculations. In the tensor network side, we have a multitude of techniques to work with. There's free probability theory, there's numerical analyses, there's resolvent techniques and so on. And so all of that can now be applied directly to the gravity situation, which wouldn't have been obvious from the gravity side just because we don't know exactly what to integrate over, what to do and so on.
For these particular
fixed area states, but then, so very often what ends up happening is related to what Fonkar was saying. If you want to compute things in general states, you can write them as a superposition over fixed area states, and then try to argue that whatever there will be some relation between what you computed for fixed area states and what you compute for general states. So for example, in these phase transitions, people have used this precise thing to compute like detailed corrections near the phase transition. So the way you should think about it, I think, is that the tensor network, like these fixed area states or random tensor networks, provides a useful basis. Like you may not care about these states directly, but they're useful sort of routes to get to the thing you get.
So I'm hearing that the tensor networks give you some useful mathematics to analyze gravity path integrals.
Yes.
Okay, that's fair.
Yeah.
Just to understand that, sorry, this is great not to be too skeptical or anything without understanding it. But I mean, so take your exchange dominance example, yes. Right? I mean, well, I can always compute the extremal surfaces anyways. Suppose I was a skeptic, hard nose. Okay, I can compute everything using the known rules of gravity path integral. So what do I mean?
I don't think we understand the laws well enough. Like how do you?
Give me a boundary condition which is
sensible. You can find the saddle point, like that's fair.
And I can compute one loop determinants, unlike your fixed area guys, they'll all be under control.
Yeah, okay. But I don't think so the things that become important near the entanglement phase transitions are not the one loop effects. What becomes important is the non-perturbative effects that you get from this.
So I compute those. Otherwise I do my gravity path integral with fixed boundary conditions. If it can't be done, it can't be done.
No, like in the only case where we actually know how to do that is like JT gravity or something. Like we don't really know what to integrate over in high
But
dimensions.
then you're telling me I don't know how to do quantum gravity.
That's right.
Random tensor networks aren't going to teach me how to.
No, but they're making specific predictions. So like like the random tensor network is teaching you how to compute something in the sense that we know. So we made an indirect connection, right? So random tensor network was related to fixed area was related to general states, and then we computed something about general states. This is something that you can do without knowing about the rules for the path integral, just because we know what the rules are for the tensor network.
So give me an example where quantum. Let's say I'm working in a situation where G Newton, so to say, is not a large parameter, or n is order.
Oh, it's a finite thing.
So I thought that's what you meant. You said.
Well, we're always working in like some asymptotic expansion.
No, then what is? I mean, not to be too skeptical, but just give me an example where I am a lowbrow gravity physicist. I know how to do gravitational calculations as saddle points plus loop corrections, let's say. And there's something I can't compute, and the random tensor network tells me, do this calculation, and moreover, here is the result. That would be really striking, right?
So, let me give you an example of this.
Don't mind.
No, that's fine. So let's say you wanted to compute exactly something like this, where you have two extremal surfaces and you want to compute the entropy, and you're near the phase transition, not anywhere far from the phase transition. Not like.
Okay. Just to understand, the phase transition
is when these areas are similar.
I'm changing. Yes. Okay.
Yeah.
Excellent.
So good. So now, on the gravity side, the only case where we actually know how to do that path integral is like JT gravity. So in PSSY, like in the.
Let me just stop you. Suppose I take a standard situation which has ADS-CFT, okay, where curvatures are small compared to G Newton, okay, etc. I know how to do that path integral reliably in the semi-classical approximation.
In the saddle point approximation.
If there are two areas which are comparable, they're comparable, okay? I mean, what is the breakdown there that you're talking
but like what saddles are you going to include?
I'll include both of them.
Oh, you're good. So that'll give you the wrong answer. So that's what I was getting. So there's two saddles you can write down. There's two liquids Madisena, like replica symmetric saddles that you can write down.
Yes.
That if you take those naively, just take the sum of those two and try to compute the entropy from that, you get the wrong answer. This was a calculation that Rob Myers did like 10 years back or something.
And wrong meaning, how do you know
it's wrong? Because it gives you. It doesn't even make sense in the what it gives you.
Why doesn't it make sense?
Yeah, what it gives you is.
I don't know this. Yeah.
So if you compute the entropy, what it gives you is basically half of the. Let me call these areas A1 and A2. So let's say one of them is A1 and one of them is A2. If you do this thing that you said, then what you end up with is half of A1 plus A2. Which is very far from and this calculation is applicable no matter how different A1 and A2 are, right? You're just all you're doing is taking the path integral, you include e to the minus I1 plus e to the minus I2, where I1 is the contribution from one of the replica symmetric saddles, I2 is the one from the other one, and then you end up with this answer. This answer is very wrong from the.
So this is applicable only when A1 and A2 are close.
No, this is not.
Because you have to take log and stuff, right?
Yeah. That after taking the log.
How can it give you that? One of these will dominate, right?
Oh, so it depends on what we're doing here. So are we taking G goes to 0 first or n goes to 1 first? Because there's also an n here, so there's an n minus 1 in front.
I was doing the following, you can tell me. I was keeping n to be some big number. I was changing.
N to be some big number.
Right.
Okay.
G Newton to be a small.
Oh, sorry, capital N you mean. For me, like there's a Renyi parameter. Cn is.
Renyi parameter. No, I'm just computing the entropy as a function of interval size.
Sure.
By summing over all samples.
Right, but the only way we know how to do that is to first compute the Renyi entropy and then analytically continue.
Okay. Okay, if you like, sure. But otherwise, I'll just compute the areas. But okay, we'll do it your way. We'll do it your way, just to be careful. Okay. So your little n is very close to 1.
Yes. So let me just write down. So there's one of them is going to be like n minus 1 a1 over 4g, and the other one is going to be like n minus 1 a2 over 4g.
Yeah. And then what I was doing was I wasn't keeping track of little n, but let's say we keep n minus 1 as some small fixed number, and I dial the length of the interval. So then it's because this quantity is determined by data, which is ultimately
sure. That's all in A1 and A2.
So I dial it
Yeah.
till A1 gets comparable to A2.
Sure.
Then I add these two. This is the answer.
Yeah, that's what I'm saying. So now what we do to compute the entropy is just take the derivative and the derivative at n equals 1. So if you took g goes to 0 first, then before taking n goes to 1 or like computing this derivative, then you just drop one of the contributions. Like they won't even matter.
And that's a sensible looking answer.
That's a sensible looking answer. That's the Lukowitz-Manderson answer.
Yeah, then
Now you're saying you want to do something better. You want to find like corrections to that.
Yeah, no. What I would have thought is that the more general prescription coming out of gravity is always obtained by ultimately appealing to ADS-CFT. So what ADS-CFT says is that the replica trig path integral on the boundary is ultimately a path integral, and every path integral in the bulk can be mapped to a path integral in the every path integral in the boundary can be mapped to a path integral in the bulk subject to correct boundary conditions. Good. So I do that map, okay? Yeah. And then the question is, how do I evaluate the bulk path integral? Good. Can I evaluate it or not?
Yeah.
But the rule to do it is given by
in principle, yeah.
So either you're telling me that rule is wrong, or you're telling me somehow, although it's hard to do that path integral in quantum gravity, you can give me an answer to it.
Yeah.
I doubt. I mean, are you telling me that a gravity path integral, which has to be done and which cannot be done by the usual rules, okay, root GR path integral, the answer is coming out correctly in random tensor?
It does. That's what I'm telling you. So.
Actually, just to say, I mean, it sounds like you're saying that if you take that path integral, gravity, and break it up into constant area states and integrate over those areas, that's what's giving you the right thing, right? The random tensor networks is just some mathematics. I mean, it's just some permutation.
Okay, good. So
let's forget random tensor.
Okay, we can forget about it. Yeah.
Okay, we can forget about it. On the last step, I mean, if you will be able to compute these things for fixed area states,
which is strange.
Yeah.
You can't do the
these are not linear
I know that's right. So that's what I was telling Omkar before. So that's what I was telling Omkar before, which was that there is an argument which was like by Akers and Pennington, which tells you that you can still approximate. I mean, it's a story that goes back to like Almeri, Dong, and Swingle in 2016. The fact that for these large N systems, the entropy roughly behaves like a linear observable. There's a very concrete sense. So there's an upper bound and a lower bound you can put, which gets sandwiched at large N. And that tells you that at leading order, the answer you get from fixed area states is very closely related to the, by taking a superposition is just literally just the linear. That's a non-trivial step.
So going back to something, what is the question that you cannot quite answer for, let's say, vacuum states, but you think of vacuum states as a superposition of these fixed area states, you can answer that question?
Yeah, that's what I'd like to answer. Just from semi-classical gravity, how is it that doing some Fourier transform helps you do something that you could not do?
It seems like you've done a Fourier or whatever transform, and now you are able to do the calculation in gravity, which is otherwise difficult to do. I mean, how did that happen?
I mean, in principle, I guess it was always doable, but like, we don't really know how to do any of this. Like, I mean, already at the Lukowitz-Manderson level, right? Like, if you wanted to compute the Renyi entropy at some n, in principle, it's doable, but like, there's basically no situation where we can do it.
It's very
so if that's what you mean, then in principle, this was also doable.
No. But how in practice was it possible?
In practice, because we could exactly write down these saddles.
Yeah. So this is what I'd like to understand. You're saying semi-classical gravity. This is just a trick in semi-classical gravity.
You can say that.
Okay. In semi-classical gravity, there's a new trick which involves these fixed area states that allows calculations that were otherwise not possible to be done.
For vacuum state.
For any state,
It seems something like this. Because sometimes you have these constrained instanton problems.
It's exactly like a constrained instanton.
That's what it is.
It's exactly like that. So like you should think of the area as the constraint.
Yeah, it suggests that. So it's some situation where before you were close to the phase transition, you didn't, you had a nice instanton anyway. But because you have two, you may be able to interpolate between them or something, and now the original semi-classical approximation is not good, and this one becomes good with the constraint. It is such a, I don't understand it from the gravity.
I mean, I think in the end you could say that, like, as long as you were smart enough to write down like the fixed area states directly in the gravitational path integral, which is just a Fourier transform of this constrained instanton, do the calculation, and then do the calculation for the states you care about, let's say superpositions over these fixed area states, you'd get that answer. It's just that we wouldn't have thought about writing these fixed area states without the tensor network. That's the only thing.
Not to denigrate the tensor network.
Thank you.
We're just trying to understand.
Where is the logical flow of information?
So the
logical flow of information, as far as I can see, is you've found a new manipulation of the semi-classical gravitational path integral.
Yeah.
The mathematics, we can do combinatorial mathematics ourselves without tensor networks, right?
I mean, like, I guess
that may have motivated you to do this, but the mathematics doesn't seem vastly difficult.
Yeah, I don't know. Well, I think no one ever thought about the path integral in terms of fixed area states for independent reasons. That's all I'm saying.
That is the key innovation, not the mathematics of the tensor network.
Oh, yeah, sure. I mean, I'm just saying that the mathematics of the tensor network just matches on directly with these fixed areas.
It's very nice.
That's all I'm saying.
That's the motivation.
That's the only thing I'm using it for is to say there's a duality between these two things. Once you know that, then do whatever you want with
That's very nice. But just to understand, the thing that seems really interesting to me is that you found a new trick in semi-classical gravity that I didn't know.
We can say that.
So I would really like to understand that. Maybe.
Maybe you can say, like, what is the calculation that will let this trick will let you do that you wouldn't have otherwise?
That's what
I was getting to that.
No, that was this near the transition.
Which is the near the transition entropy.
I frankly have not understood this figure.
This figure, good. So
neither me.
So what we were drawing?
Maybe we should start
Next time.
Should I just complete this? I mean, this was like my last slide for this part of it. So if I just, so the figure was, so in the Pac-Man geometry what we were drawing was, so this was your region R, which was the boundary region, and you were tracing out over some region. This was gamma R, which was the unique extremal surface in that case, right? Now let's consider a situation where it has multiple extremal surfaces. So I start with, so there's a gamma 1. So let's say I was computing the entropy of this region. Then there's a gamma 2, which is the outer extremal surface, which is here. So the traced out part sort of ends there. And then there's gamma 1s on each of these surfaces. Right? That's this pentagon picture.
So there are two sources.
There's two sources. Yeah, there's two sources. That's this pentagon picture. So now I'm computing like trace rho to the 9th or whatever.
I'm sorry, in this pentagon, which is 1 and 2?
So this one, the one which is in the middle, is gamma 2. And these two, like these two, are gamma 1.
Okay.
So basically, you can figure out by which one's closer to the boundary. Okay. So these pentagons, now I just want to compute trace rho to the 9th. We just glue them together, and based on the previous argument, we saw that there's a full class of saddles which are just like different gluings of this. The different gluings are just labeled by permutations. So it's just different ways in which you glue these patches together.
You're supposed to glue different gamma 1s.
Yeah,
and different gamma 2s.
Because you wanted them to glue together, so they're different areas in general.
But gamma 1 can glue to one guy and gamma 2 to another.
Other guy, yeah, exactly. So, like for example, here your gamma 2s are just gluing to each other, but gamma 1 is gluing like in a cyclic fashion. So essentially, there's a one-to-one map between like, and for good reason. I mean, it's just like naturally the same. It's just labeled by the set of permutations, which is exactly what the tensor network was doing. No back reaction, one-to-one mapping, so you get the same answers. That was the main point.
Yeah, but you know what I would find really interesting, Pratik, is to just try to see, like in context of a particular example, to try to see why it was difficult to do it without this Fourier transform, and why this helped.
I've never quite gotten a gravity example like that.
Yeah.
I understand constraint instantrons engaged theories and so on. And I know what happens there because you have an underlying scale.
No, so you can do this calculation. So whenever you can actually do the path integral, like for example in JT gravity, you can actually do the full calculation and the fixed area calculation. You can do both of them.
No, but I was saying just this two interval in ADS5.
Yeah. In ADS5?
Yeah.
You're saying
I think it's just in practice impossible.
Yeah, but what is the, I mean, can we sort of see where?
I mean, I would have just thought that you keep the solution to the classical equation subject to small whatever deficit angles.
Yeah.
And you get what you get. I mean,
you get what you get. Yeah, it's just
that's wrong.
What's the right answer? The right answer is like, so there's large correction. So it basically ends up being an average. So there's some these coefficients that I was writing down. So we had the sum over ICI, like these sort of fixed area states give this basis. In the end, all you need is, it basically behaves linearly. So the entropy of rho is approximately sum over I mod Ci squared S of rho I. This is also only approximately so maybe there's also an issue with that step. Like it's not an exact rewriting, it's an approximate rewriting, so that might be an important point. But in the end, it's this. So what ends up happening with these CIs is, like, if you're far on one side of the phase, these CIs will roughly behave like, they'll depend on the difference of areas. So if you're far on one side, then one of them peaks, and if you're far on the other side, then the other one peaks. But in between, it's like a mixture of those. So roughly the answer in the end to some approximation just becomes the expectation value of the area in this sense. Like there's different parts of the wave function where different areas peak. And in each of them, you just evaluate the RT formula.
This approximate things coming because of
Seems like
cross terms, or
Sorry?
are they outside?
Yeah. There are cross terms. So in general, what's true is in general, S of sum over I rho is upper bounded by sum over I. Sorry, let me write E I rho I. It's upper bounded by the this plus Shannon term, and it's lower bounded by just the average. So there's always this Shannon term room to play, and that's related to the off-diagonal terms that we talked about. So, but the important point is that the Shannon terms are typically like logarithmic in G. So they're subleading, and at leading order, so these near the phase transition, the corrections happen to be order 1 over square root G, and you get up to that, like these Shannon terms don't matter, so you get sandwiching on both sides.
So S of rho is of order 1 by G, and these are
S of rho is of order 1 by G, and you can like compute it accurately to order 1 over square root G if you like. The corrections don't affect that.
Is basically what's going on, that it's confusion about whether n goes to 1 first,
Yes.
or g goes to 0 first.
Yes. So essentially the thing that we got out of this was, what you learn is that the thing you were saying was take the two replica symmetric saddles and just add them and compute whatever you want. That's the wrong prescription because you're missing these replica symmetry breaking contributions. So there are arbitrary permutations you can apply, right? So there'll be like non-replica symmetric permutations as well that you can apply. All of those contributions, when you take the areas to be closer and closer, they all get sandwiched. So they all contribute roughly equally. They're all important. And so that was the thing we're missing from that calculation. So that fixes up this Myers problem.
So basically, even if, if you actually go back to Lukowitz-Mandelsena derivation, you are supposed to take into account all the saddles.
You are.
Right? But the RT formula kind of
is simpler.
But here, in some sense, even though you use fixed area states, you can still take into account all the saddles because they are kind of easy to
Exactly. Back reaction is controlled.
Produce maybe a little bit wrong answer, but at first order the right answer.
I think that's a fair answer.
Okay, so now if it is a matter of, if you did, that's what I was trying to say. At root, what Lefkowitz-Mandelsena first starts with by saying is, look, we are only returning the rank of ADS-CFT. I have a path integral in the boundary. I'm just mapping it to a path integral in the path, right? That's ADS-CFT, that can never fail, right? The second step they say is, okay, we assume a particular kind of saddle dominance, right?
That's
okay, that step is failing, but it seems to me that perhaps what you're saying is, there are other saddles which we did not include, which need to be. Or is it more?
I don't know if there's a controlled sense in which we could have. Maybe if we had enough control on the path integral, then maybe there's a controlled sense in which we would say, just find all of these other saddles, add them up, and you just get that answer. Like for example,
if it's a departure more than that?
No.
Then I'm like, my head's...
No. I think it's exactly that. I'm just saying that you should think of this as a technical tool. Like I'm not saying it's like giving you a new theory if you want to gravity.
The reason I'm saying is in constrained instantons, to the extent I understand it, so if you don't put the constraint, you don't have a saddle.
If you don't...
because you have the scale invariance of the theory, etc.
Yes.
So to get a saddle point, you put the constraint.
Right. This is slightly different from that. Like you get a saddle, I think.
You do get a saddle, but it's a replica.
Actually,
it seems.
So in this replica symmetry breaking cases, I think you just get you get the saddle. That's right. Yeah, you get a class of saddles. Like you get many saddles, you want to sum over all.
But like Abhijit saying, the sort of non-trivial thing is that you are able to control these these new saddles.
Yes.
And now going back, could you have just done it without these fixed area states?
I still don't know how we would do it. Like in JT gravity, we know how to do it, but that's like a very special case where we understand the path integral. In principle, there's so now that we know exactly what kind of replica symmetry breaking solutions arise, we made some attempts to look at this two intervals vacuum example. So there were calculations of this previously by Tom Faulkner, just computing the action of that replica symmetric saddle. In principle, you could generalize this thing to do more general things, but unless you get the full analytic answer and analytically continue, you don't get anything. So it's actually a very hard problem to solve, even after you know exactly which saddles you care about.
What about its two-dimensional CFD? Can you?
That is 2D CFD.
That is true.
So the checks of your answer would be from the CFT side, or
so this is actually a very general fact. So there was a paper by Mark Shrednicki and collaborators which analyzed this before all of this fixed area state stuff, where they made a prediction for what happens near the phase transition. Like these 1 over square root G corrections is basically related to specific heat and so on. There's a very general universal answer for that, and this reproduces that.
Very nice.
Since we are
all right. Thanks for listening.